full duration of this workshop, and we'll send those PDHs to you within a week or two after this workshop. If you have any ideas or suggestions for future topics or workshops, we'd be excited to hear from you. So shoot us an email afterwards at our sptc@ou.edu email address. So without further ado, I'd like to introduce our presenter, Dr. Jerry Miller.
Thank you very much, Michael. It's a pleasure to be here. Get to see some old friends I haven't seen in a while and talk about a subject that I really enjoy. So just to give you a little bit of background, I know most of you in this room know me, but maybe some folks online don't. I've been at the University of Oklahoma for, well, it'll be 31 years in August. And it's been a great career here. I've done a lot of research in unsaturated soil mechanics, where I got my start in unsaturated soil mechanics back in the early 2000s, late 90s, and have benefited by the local knowledge of a lot of folks. Dr. Jim Neville's in the audience. It was instrumental in my early career, and I'm grateful to him for that. And it's just been a great ride, lots of great students. So what I'm going to talk about today is the application of unsaturated soil mechanics and geotechnical engineering. I still think there are some hurdles to overcome in terms of making unsaturated soil mechanics more mainstream in our practice. So the things I'm going to talk about today are some ways that you can simply incorporate unsaturated soil mechanics principles into your day-to-day analysis from a very simple to the more complicated in some cases. It's not always warranted, but I think for us, especially in Oklahoma, where most of our soil profiles are unsaturated to considerable depth, every time we do a subsurface investigation or an analysis, we should be thinking about how changes in seasons and moisture conditions are going to affect the performance of the structures that we're designing to put on those profiles. So hopefully you'll have a few tidbits to take away from this that you can be thinking about and using as you see appropriate. Okay, I got to do this old school. My pointer's not working for some reason. Okay, hang on. Maybe I got to be on the slide. That's not working at all. Let's try this. Okay, there we go. First, a few acknowledgments. I'd like to acknowledge the folks that have supported my work over the years, including ODOT, the Oklahoma Transportation Center before it changed its name to the Southern Plains Transportation Center, and the National Science Foundation. SPTC for sponsoring this event, and particularly the staff. Olivia Daly was instrumental, and Michael, and I don't know how to say Lebo's last name. Did you say the N? Is it Natesso? Okay. And then some of my former students who made significant contributions to this work are Dr. Tarek Kabuwa, Dr. Rodney Collins, and Dr. Tommy Bounds. And of course, Dr. Jim Neville's was a big part of my research career and did a lot of the work alongside us, so I'm grateful to him. And Medco contributed significantly to the work that some of the work I'm going to share with you today. So, okay, so this is the schedule. This is a very tentative schedule. It could change on the fly. Sort of estimated how much time I want to spend on each of these topics. So some may take a little more, some may take a little less. First, I'm going to give you sort of a big picture view why I think unsaturated soil mechanics is important to be thinking about when you're dealing with significant unsaturated soil profiles. We'll do a little background discussion on soil suction and the soil water characteristic curve. These two things are an important part of the unsaturated soil mechanics framework. Then I'll talk a little bit about how we can determine soil suction and the soil water characteristic curve. I'm also going to spend a little time talking about stress state variables, because inevitably the differences between saturated and unsaturated behavior come down to the way the effective stress changes in an unsaturated soil, whether it's wetting or drying, and the impacts on soil behavior. After that, I'll get into some discussion on interpreting standard penetration tests in unsaturated soils. We use the SPT pretty extensively in practice. I think almost every subsurface investigation includes some SPT work. Sometimes the SPT is the only indication of the mechanical behavior of the soil that we have for a project. And so we have to think about what it means if we do that test during a dry period or during a wet season, and how that influences the interpretation of the results. Same for the CPT. And then I'll talk about something, I'm not sure how many of you folks are using seismic velocity measurements, but the seismic cone penetrometer is a very useful tool for determining seismic velocities. And those can be used, for example, looking at seismic site class or for doing ground response analysis. So it's a very useful tool. We've done pretty extensive research over the last, I don't know, we'll say decade, but it's probably 5 or 7 years, and learned some interesting things about shear wave velocities in unsaturated soil. So I'm going to spend some time on that. Talk a little bit about the influence of suction on laboratory tests, and then we'll sum it up with some takeaways and question and answers. Of course, during this presentation, please feel free to ask questions or make comments during the presentation. I'm happy to stop and discuss things. I am going to give you a break on the hour. I've got one 10-minute break scheduled at 9:50, but we'll take another intermediate break there. It's kind of hard to sit for 2 hours without a break. So that's the plan for today. Okay, so let's jump into this. First, the big picture. So why is unsaturated soil mechanics important? I'm going to demonstrate this with 3 examples. There's numerous examples we could talk about. And so the first, I want you to think about a compacted embankment. So by its very nature, compacted soils are unsaturated, right? If you compact to optimum, you're probably around, I don't know, say 70 to 80, maybe a little higher in some cases, % degree of saturation. So that means it's unsaturated, and so its behavior is going to depend on unsaturated soil mechanics. And of course, over time, these embankments can get wetted, and that's going to change their behavior. So there's 2 things we should be thinking about. How does the shear strength, I'm sorry, go ahead.
This is a very basic question, but I'm probably the only non-geotech in the room.
Oh, okay.
Could you define simply unsaturated?
Yeah, so actually I have some slides coming up, but the big difference is saturated soils are 2-phase materials consisting of soil solids and water. So there's no air in the voids. So think of soil below the water table. Soil above the water table is typically 3-phase, which means it has air and water in the voids, and of course the soil solids. So that's the difference. And it's that
the air has pretty much been pushed out by the water.
in a saturated soil. That's correct. Yeah. And the behavior is significantly different because, as you know, water is incompressible. And so a lot of our fundamental soil mechanics that we learned as youngsters was based on saturated soil principles. But when you introduce air, it's a highly compressible fluid, and that changes the behavior along with the interaction of the air and the water. That leads to what we call capillary pressure. And we're going to get into this more and more. So yeah, so the question is, how do we deal with this situation, not only for the embankment, but the underlying foundation soil, which is often also unsaturated. So if you have a rising water table and you have infiltration of water into your embankment soil, this is going to affect the mechanical behavior, which for us means it's going to change the stability and it's going to change the compressibility. And so today, I'm not going to go into great detail on volume change behavior. That's probably going to be part 2 later on. Today, I'm going to focus mainly on, my examples are going to focus mainly on shear strength. But we also need to be thinking about volume change behavior, because that's important as well, especially in unsaturated soils. We've done a lot of research on wetting-induced compression of compacted soils. And compacted soils are susceptible to significant settlement. If the embankments are high enough and the stress states are high enough, you can get this wetting-induced compression in the lower regions of the embankment, which can lead to significant settlement. I'm not going to go into that in a lot of detail, and I'm not going to go into expansive soils today. I think in practice, that's the one area of unsaturated soil mechanics that people are pretty well versed in, is expansive soils, but there's still a lot to learn there. And in a future presentation, we might go into those aspects of unsaturated soil behavior in more detail. So, okay, so back to my example. So we need to be thinking about changes in shear strength and how that affects the performance of our embankment, and also how it affects our stability analysis. And then, of course, there's the compressibility and the settlement of the embankment. Another example to think about, and this one I'm going to get into in some detail today, is, if you think about our subsurface investigations, we don't have a lot of control over when we do those. The client wants you to get your drill rig out there within the next 2 weeks or month, so you do it. Well, what if you're in an extended dry season? What if you're in a drought? We have droughts sometimes that last 5 years. You're going to be testing unsaturated soil profiles and potentially sites that have fairly deep water tables. And so the question is, what do those SPTN values mean in terms of the design? So let's suppose we get SPTN values and we use those as the basis for analyzing the bearing capacity of a footing. And we could also extend that to, say, the settlement. Well, the behavior of that footing will be fine as long as those moisture conditions don't change. But suppose the drought breaks, we get significant infiltration and rainfall, and now the conditions have changed, either before construction, sometimes construction is a year later, or during construction. How's that footing now going to behave now that we've designed it based on dry conditions? So we need to be thinking about those changes and how that affects the performance of our structures. Generally, from a bearing capacity point of view, we often get away with it because we're so conservative in our allowable bearing pressures anyways. But it makes a difference. You need to be thinking about it regardless. Another example, and I don't know if you've thought about this, a lot of us provide L-pile parameters. When I say us, I mean geotechnical engineers. I do a lot of consulting and have done it my entire life, so I'm pretty familiar with aspects of practice. And I know one thing clients often want is L-pile parameters, so they can run their L-pile analysis and design their drilled shafts and piles. So we have to give them soil properties over the full depth of the embedment length. That means that portion that's in the unsaturated soil profile. And so, for example, in a clay, we have to provide estimates of undrained shear strength. I don't really like to refer to undrained strength in an unsaturated clay, but we often do what's called the total stress analysis based on undrained strength principles. And so if we're basing those on SPTs or unconfined tests from that unsaturated soil profile, again, they might be valid for this dry season condition, but what happens if we get lateral loading under a different condition, when the soil ground conditions are wetter? And so that's something we can also be thinking about when we provide L-pile parameters, or for L-pile or any application. How should we adjust those depending on anticipated moisture conditions and moisture conditions at the time of our subsurface exploration? So these are the main points I want to stress today. And I'm going to show you some data that sort of illustrates how these things change with changing moisture content. Okay, some important points to be thinking about as we go through this presentation today. First of all, most soil profiles contain a near surface zone of unsaturated soil. I would say that's especially true in Oklahoma. Certainly there are profiles that are saturated, depending on where you are in the country and where you're located relative to floodplains and rivers and things. But a lot of the soil we work in around the central Oklahoma area, it has a significant unsaturated zone. So what happens in these zones as the soil desaturates, so let's say a soil profile starts saturated and then it drains, it desaturates, the pore water pressures transition from positive to negative. So if you remember your effective stress principles for unsaturated soil, effective stress basically controls all aspects of mechanical behavior, and it's equal to the total stress minus the pore water pressure. So if the pore water pressure goes from positive to negative as the soil dries, the effective stress increases. Well, that's good from a mechanical behavior point of view. It means the soil is going to be stronger. But if the opposite occurs, you go from dry to wet, now your pore pressures are getting more positive, and you're going to have decreases in effective stress, which is going to make the soil more compressible and less strong. Okay, the magnitude of negative water pressure varies with the soil water content. So as the soil gets drier, that negative pressure increases or gets more negative. And then negative water pressure, or what we call matrix suction, which is actually defined as the difference between pore air pressure and pore water pressure. In many soils, the pore air pressure is zero. It's at atmospheric pressure, that's zero gauge pressure. That means the suction is essentially a measure of negative water pressure. That's particularly true in sandy soils. And it has a profound influence on the mechanical behavior. And you're going to see that through some of the data that I present today. Okay, some other points to think about. Seasonal variations in moisture content, therefore, have a profound effect on soil behavior. Many of our structures are founded in the unsaturated soil zone. Slabs on grade, spread footings, pavements, anything that rests on top of that profile and derives its support is going to depend on the behavior of that unsaturated zone. And I should mention pavements, since this is a transportation seminar, those as well, if I didn't already mention them. Compacted soils are unsaturated and subject to significant changes in behavior due to post-construction changes in moisture content. Years ago, with the help of Dr. Nevels, my research group went around and looked at embankments, highway embankments, that had significant increases in moisture content. We also looked at embankments that were constructed in reservoirs that were then impounded, because that's the classic case of wetting. But even these highway embankments that are nowhere near water saw significant increases in moisture content just from infiltration. Water gets trapped in that granular layer below the pavement and slowly infiltrates into the embankment. And Jim actually provided some great data that showed significant increases, like 4% changes in gravimetric water content in a compacted embankment. That's significant. And as a result, these embankments experience significant wetting-induced compression. So we can't think of compacted soils just because they're engineered soils and we get them to 95% of standard, doesn't mean they're going to behave real well because of wetting. We've done a ton of research on soils, compression behavior of compacted soils, compacted to 95% of standard Proctor. And they can experience up to 7% strain due to wetting, which is a lot. If you think about an embankment that's 30 feet high or more, that's a lot of settlement. And we saw settlements on the order of a foot or more. So it's real important to think of compacted soils as unsaturated soils subject to changing behavior due to changes in moisture content. And then this is sort of the big takeaway. Geotechnical engineers should consider how water content and suction impacts their lab and field tests and their design recommendations. Okay, so now some basic concepts to go along with this. On the left, you kind of see a depiction of a soil profile. At the bottom part of the figure, you see we have our, is this working? Oh, that's one of those screens that won't take a laser pointer. At the bottom part of the soil profile, we have saturated soils below the water table. And you'll notice that the pore water pressures, which is indicated by this line, are positive below the water table. At the water table, they start to become negative. This is the capillary fringe, which is in a near saturated condition. And so if the pore water pressures were hydrostatic, that line would just continue straight to the ground surface. But generally, they're not hydrostatic. And you get into this part, they may be in the capillary fringe because it's near saturation. But as you get above that, you have deviations from that hydrostatic pressure line. So your negative pressures during a dry season can get quite negative. And if you have wetting events, then the negative pressures are reduced. So you see this variation in moisture content generally about that hydrostatic line as the water content changes in this zone. So this is the zone we're interested in. And on the right is just a little taste of what happens as the water content changes. What you're looking at here is the tip resistance from a cone penetration test, friction ratio, and then water content and the capillary pressure matrix suction. And what you see is there's a wide variation in the water content over the dates of testing, which span a couple of years. And you'll also notice that the largest variations occur near the ground surface, and then as you get deeper, the variations are smaller. And that sort of points to this concept of what we call the active zone. So the active zone is that depth from the ground surface where the soil moisture varies seasonally or even beyond seasonally. So in droughts, it may get even deeper. You'll notice in my data there, it looks like the active zone may be around 2.5 meters, which is that's probably close to 8 feet or something like that. But it can be deeper depending on what kind of weather conditions we're in. So when we analyze the changes in soil behavior in the unsaturated zone, we are looking at that active zone to try to figure out where these changes are going to occur. I think many of you are familiar with this concept from your PVR analysis. We have to assume an active depth to do our analysis, and that's the depth where we assume wetting is going to occur and heave is going to occur within the soil profile. So it's important to think about the active zone. The other thing to think about with regard to the active zone, and I've seen this in a few cases, sometimes while the natural active zone may be 8 to 15 feet, you can have unnatural wetting due to changes in surface water hydrology or subsurface hydrology, changes in man-made problems, broken pipes, irrigation, things of this nature that will actually increase the depth of wetting or even the degree of wetting within the active zone. So those are things to also keep in mind when you're defining your active zone, doing your analysis. So, and by the way, these figures are from Dr. Fredlin and Dr. Raharjo's book, Unsaturated Soil Mechanics. So this is a sort of another shot of that unsaturated soil profile showing the nature of the various phases within the soil. So, and this alludes to your earlier question, below the water table, you have water filling the voids. Air is primarily in a dissolved state, so it's dissolved within the water phase. In the capillary fringe, you may have a discontinuous air phase, which basically means there's bubbles of air in the water. And then as you get into the above the capillary fringe, you have primarily two fluid phases. The air in the water phase can be continuous, which means that you have continuous pore air channels and continuous pore water channels within the soil. And then if it gets really dry, you can have a discontinuous air phase. So you can be thinking about these different zones, and obviously these borders can change depending on weather and position of the water table. The reason this is important, as you'll see when we look at what's called the soil water characteristic curve, the magnitude of this suction is going to change depending on the water content, and so is the behavior. So that's why this is important. Okay, so I'm going to pause there. That's the first section. Are there any questions? Okay, we'll continue on. So now we're going to talk about soil suction in the SWCC in more detail. Okay, so how do we define suction? So getting a little technical, it's defined as the free energy state of soil water. Now the units of suction are pressure. Pressure is actually a measure of energy of a fluid or gas. So basically total suction is the free energy. And it can be expressed in terms of the partial pressure of the pore water vapor relative to some reference state. All right, so you might be thinking, why is it related to the partial pressure of the pore water vapor? Hopefully the next slide will help to clear this up. And just to give you a little insight into why this is important, we use this concept and the corresponding equations that describe it to measure total suction in soils. Okay, so here's a comparison of our soil system to what we call the reference system. So whenever we're looking at pressure or energy, it's always relative to some reference system. Even pressure that we measure, air pressures or gas pressures or whatever, water pressure, it's always relative to atmospheric pressure. It's gauge pressure. So there's always some reference state involved. When we look at suction, the reference system is shown on the right. I keep wanting to use that pointer, but it doesn't work. And what you have is basically what we call free water. That means that water is unaffected by chemicals in the water, like salt ions, and it's unaffected by the container that it's in. So it doesn't react with the solids. So those water molecules are unimpeded by chemistry or solid water interaction. On the left, we have our soil system, and this water is influenced by its interaction with the solid. Okay, that's that capillary effect. And if there are ions in the water, as there often is in natural soils, there's usually some salt content, those also affect the water and the water molecules. So at equilibrium, and that's how we measure this suction, it has to be an equilibrium condition. At equilibrium, the rate of evaporation of water molecules equals the rate of condensation. What that means is that the energy state of these water molecules in the vapor and the water are the same. So if we know the energy state of the vapor, we know the energy state and the suction of the water phase. And that's what we're interested in, right? Because it's the water phase that's interacting with the solid and affecting the stresses. Does that make sense? Okay. So then based on this, and I'm not going to go into the details of this equation or its derivation, but this is the thermodynamic equation that defines total suction. And so it's based on the kinetic theories of gases, but what it boils down to is that term in the brackets at the end, that's the partial pressure of the pore water vapor over the partial pressure of the pore water vapor in the reference system. By definition, that's relative humidity. The terms to the left of that are pretty much constants. Now, temperature can change, and that's one thing to keep in mind when you're using measurements that depend on this equation. The temperature is important. I don't know how many of you are familiar with, say, the WP4 chilled mirror hygrometer. I'll show you this later. But it actually controls the temperature of the environment where the measurement is made, because the equation is very sensitive to temperature. But the other things are constants. So the idea here is if we can measure the relative humidity, and we have devices that do that, we can measure this total suction. Okay, so that's total suction. Now, total suction is not matrix suction. And this is important to realize, because if we're measuring total suction, we can't assume that that is the matrix suction unless there happens to be no salt or chemicals in the water. If it's pure water, then total suction equals matrix suction. But the presence of salts affects the energy state of those water molecules. And the problem is this what we call osmotic suction that results from the dissolved solutes does not have the same physical effect on the stress state as the matrix suction, the capillary portion of that. And really, it's the matrix suction that's of most interest to us generally in terms of looking at mechanical behavior of soils. Okay, it's that if you look at my sketch over there, you'll notice that water surface is curved. And that's due by and large to that matrix component of suction. That creates the pressure difference between the air phase. So if you imagine the air above the water, let's assume it's at atmospheric pressure. The water, because there's suction, matrix suction is in a negative, has a negative pressure. And that's why the surface is curved, because that air pressure is pushing down on that interface and causing it to curve. And so it's important that we distinguish between these two when we're making measurements of total suction, if we're trying to model the mechanical behavior of the soil. So the osmotic, that's those salt ions do affect that energy state and that pore water vapor pressure, but they don't have the same influence on the mechanical stress, okay? All right, so just to give you some sense of what osmotic suction may look like, and it may have, you know, it's not that salt doesn't affect soil behavior, it does, especially clay soils, not so much in sandy soils, but in clay soils, the salt is going to affect the diffuse double layer, those films of water and ions that surround our clay particles. But you can have diffusive forces acting within this structure that can affect the behavior, more so in clays than in salts. But basically that picture on the right sort of illustrates what osmotic suction might look like. So if you have a semi-permeable membrane separating soil water from free water, water without ions, so that membrane lets water molecules pass, but it doesn't let the salt ions pass. So what happens is you'll see the level on the saltwater side is higher, and that's because of that diffusion force. There's less concentration of water molecules on the soil water side, so water molecules are diffusing into that side, and that's what's causing that osmotic pressure. Okay, a little bit more about matrix suction. So how exactly does this capillary pressure develop in soils? Well, it's very much like capillary pressure in a capillary tube. So on the right, you have a glass tube submerged in water. And maybe you've done this experiments when you were in school or seen it before. If you put a straw in a soda and you hold the top and lift it up, the fluid stays inside. That's essentially capillary pressure. So what is it? Well, what happens is the water interacts with the sides of the glass tube. Matrix forces, there's essentially a force of attraction between those water molecules and that glass tube. And so the water creeps up the glass tube, and as it does, because the water column is getting higher relative to the zero reference plane, the pressures get negative. So the pressures at the top of that capillary, at that meniscus, are actually in a negative state. Well, in a soil, the same thing happens, and here's just a simple illustration of some spherical particles. You can imagine sand particles. As the water dries, the water recedes into the contacts. So those pore spaces between the particles act like capillaries, capillary tubes. In fact, sand is glass. Glass is amorphous sand. We make glass out of sand. So there's those matrix forces exist between the sand particles and the water. And as that water recedes into the contacts, that curved surface gets smaller and smaller in terms of its radius. On the right, you'll notice the equation for the capillary pressure. It's equal to 2 times the surface tension of the water times cosine theta, which is that contact angle between the meniscus and the glass. And that's equal to rho WGH, which is essentially your water pressure. So, but if you look at that equation, what's important, you'll notice that that UA minus UW is inversely proportional to the radius of the capillary tube. So a smaller tube, the rise will be higher, the negative pressure will be higher. What that means in terms of soil mechanics, the smaller the pore sizes, the higher the negative water pressure you can generate. So capillary pressures in clays can be very high, whereas in sands, they tend to be much lower because the pores are much larger. The other thing it affects is how the capillary pressure changes during drying. As I said, as the soil dries out and this meniscus recedes into the contacts, the curvature is going to get smaller and smaller, meaning R is getting smaller and smaller, and suction is going to increase. And so here's an illustration of capillary rise in soils having different pore sizes. And so, and capillary rise, as we know, occurs in natural soils, right? That's the capillary fringe above the water table. Capillary rise is also associated with the development of frost heave. You get a zone of capillarity below the ice lenses that feeds into them. So it does occur, and it tends to be much higher when you have a much smaller pore size. Okay, so next thing we're going to talk about, any questions? Next thing we're going to talk about is the concept of the soil water characteristic curve. So as we just discussed, as the radius of curvature of our capillary meniscus decreases, the suction goes up. Okay. So what that means in terms of our soil, if we think of it in terms of water content, as the water content decreases, those capillaries are going to recede into the smaller and smaller pores in the soil, and the suction is going to go up. So we can create a relationship between the water content and the suction, UA minus UW. Over on the right, that graph is one way to portray the soil water characteristic curve. You can use any water content variable that you like to look at that behavior. What gravimetric water content is sometimes useful. Volumetric water content versus suction is in many applications very useful. So there's different ways to look at degree of saturation versus suction. But the point is, as the water content increases, no matter how you represent it, you're going to get a decrease in suction. And conversely, if the soil dries out and water content decreases, you're going to get an increase in suction. Okay, and that's important to think about because in natural soils, we're concerned with the changing moisture conditions and how that's going to affect the stress state and the behavior of those soils that are supporting our structures. So just to give you some sense of how this might look in a laboratory test. So we have, and I'm going to show you some examples of laboratory tests that we can use to determine this. This sort of illustrates the process. So in a typical soil water characteristic curve drainage test, you start with a drained condition down here in the lower right corner, your lower right side there. That's a saturated state. And so to change that suction, UA minus UW, there's different ways to do that. So remember, suction is the difference between UA and UW. So to control it, we could either change UW, or we can change UA, or we can change both. Kind of like effective stress. As long as you achieve the target value you want, the behavior will be the same. So often in these types of tests, we'll increase UA to create the suction. So as you increase the pore air pressure, you're increasing the suction, the difference between UA and UW, and initially nothing happens. The degree of saturation stays 100%. And that's because those capillary meniscus at the top of that soil, they resist the infiltration of air into the soil. Eventually, looking above that, air will start to penetrate into the soil. That's called the air entry value. So soils will resist inflow of air until that air entry value is exceeded. That means the suction at which air will now infiltrate into the soil pores. And so then from this point, that's the air entry value, the soil begins to desaturate, air is pushing into the soil, and then eventually you'll end up in what's called a residual water state, where essentially the water becomes discontinuous. So we have devices that can actually go through this process and determine this drainage curve, this soil water characteristic curve. And there's other ways to estimate it, but this kind of gives you a visual to think about what this curve means. Okay, so a couple of points here. Soil behavior changes with changes in suction, as we've discussed. So as suction increases, the behavior is going to be considerably different. And the soil water characteristic curve describes how that matrix suction changes with water content. And it's very different depending on soil type because of the difference in pore sizes. So here's some data from the literature for a silt loam, a loamy sand, and a dune sand. And you'll see for the dune sand, the maximum suction, well, as we approach residual, we're between 10 and 100 kPa. But for the loamy sand and silt loam, the suctions are much higher, and the range of suction interest is much higher. So that's an important thing to think about. Unsaturated or changes in water content have a much more significant effect on clayey soils, fine-grained soils, than they do on coarse-grained soils, because the range of suction of interest, it tends to be much smaller in the coarse-grained soils. Okay, another thing to be aware of is that that curve is not unique. It depends on the direction of the process involved. So this is your drainage curve. But if you get to the end of your drying process and then you re-wet, you end up with a different curve that's called hysteresis. And the reason for that, well, there's several reasons, but basically it could be due to trapped air in there, changes in the contact angle between drying and wetting, things of that nature. All right, so how do we go about determining this soil suction? We're going to take a break here in about 10 minutes, so hang with me and get a little stretch and some coffee and so forth. So what can we do to measure suction, and how can we determine the SWCC? So there are several ways to do it. Suction can be measured directly or indirectly. So direct measurements would typically involve the use of what we call a high air entry stone. And I'll explain what this is. And the devices that incorporate these for measurement would be tensiometers. Pressure plates are used to control suction and measure the soil water characteristic curve. There are devices that measure relative humidity. Remember the thermodynamic equation for suction, such as psychrometers and chilled mirror hygrometers. Those are used to measure total suction. And then there's indirect measurements. The filter paper method correlates the water content of a filter paper, either in contact or in close proximity to a soil sample. You can use the weight of the filter paper and correlate that to suction using a calibration curve. And then there's thermal conductivity sensors. So first we'll look at tensiometers. So the tensiometer, a couple of examples are shown here. The big one on the right here, this is what's called a jet fill tensiometer. These are handy for use in the field. And then on the left, we have a small tensiometer, which is mainly for lab applications. Both use the same principles. And so you'll notice at the bottom of each of these tensiometers, there's this higher entry porous stone. So it's a specially constructed ceramic with very small pore spaces that allows the separation of water and air and allows you to measure negative water pressure in the soil. So you can see the installation there has a pressure gauge that measures negative pressure. Now, the limitation with these devices is that they can only measure theoretically up to about 100 kPa suction. Anybody know why? So think about 100 kPa suction means the gauge pressure, the gauge water pressure is minus 100. Or the absolute water pressure is approaching 0. What's that, Hamid? I can't hear. That might affect these, but it's related more to the state of the water, right? And I'll show you a little later a diagram that explains it. It's basically cavitation. Water at room temperature, water cavitates at about a minus 100 kPa gauge. And so what that means is the water essentially, water molecules are sheared apart and you get gaps in the system, air in the system essentially. Okay, so how does that high air entry porous stone work? Well, if we were to cut away a little piece of the porous stone, obviously that's an idealized sketch. You have water on the inside of the tensiometer. You have water in the soil, and you're trying to measure this water pressure in the soil, the negative water pressure. And for this device, we're assuming that the pore air pressure in the soil is 0, which is atmospheric, and that makes sense, right? Shouldn't be elevated under atmospheric conditions, it should be atmospheric pressure. So the way the stone works, if one of the pores in the stone is in contact with air, a capillary meniscus develops. That's a function of the air entry value of the stone or the size of those capillaries. And so the air can't penetrate. But where the pores are in contact with water, water can freely communicate through that pore. And so through this communication, you're going to get an equilibrium with the water pressure inside and the water pressure outside. So you're effectively measuring the negative water pressure in the soil. That's how it works. That's the higher entry porous stone. They range from about 100 kPa up to about 1500 kPa is the limit for your standard type higher entry porous stones. So you can sustain a pressure difference of about 1500 kPa with the highest air entry stone that's available. Okay, the other thing that we use, and I'm going to introduce this concept of access translation, already sort of alluded to it, This is the pressure plate extractor. And so in this device, you place specimens on a higher entry porous disc, as shown here, and you can see them in here. And you seal up this chamber. And, you know, you have to take sample weights to get the initial water content, usually saturate the sample prior to starting the test. And then you increase the air pressure and thereby increasing the difference between UA and UW. Now you keep UW at 0. So the pore water pressure is not negative, but you're still creating the capillary effect, because remember that matrix suction is UA minus UW. So by increasing UA in that chamber, you're increasing the suction. Be the same effect if you decreased UW and kept UA 0. You should see the same behavior. Yeah, it's kind of like effective stress principle. It's the difference between the two that's important. And so you start in a saturated condition, you increase UA incrementally, and every now and then you halt the test and weigh your samples to get the water content, and you can apply your suction versus water content and get your soil water characteristic curve. Nice thing about these devices is that you can put several samples in the device at once. Okay, this concept of increasing UA and keeping UW at 0 essentially illustrates what's called the principle of axis translation. And the idea is sort of illustrated here. Again, if you were to decrease the water pressure, which you could do, you'd reach a limit. And that would be 100 kPa suction, because the water would cavitate. And that's illustrated by the phase diagram for water here. You might remember this from your chemistry. This is absolute pressure. So that's gauge pressure minus atmospheric pressure. And this is temperature. So this is roughly room temperature, around 20 degrees Celsius. If we start to decrease the water pressure, that's gauge pressure in absolute terms. This is where we are in our laboratory. If we start decreasing the water pressure, we're going to hit this line. That's the vaporization curve. It means the water is going to boil, essentially, at room temperature. Right. Normally, when we boil water, we go this way on the temperature curve and we reach this point, and that's how we get vaporization. But at room temperature, if you decrease water pressure, you're going to boil your water, and your device won't work. So to get around that, we keep the water pressure at a constant value at 0 or above, because it won't cavitate, and we increase the UA. So we can get a much larger matrix suction without causing cavitation of the water phase. Make sense? Okay. Another device we can use to measure total suction is the chilled mirror hygrometer. If you have the WP4 device in your lab, it's a very handy tool. We have one in our lab, but they measure total suction. And so that's, again, they measure the total energy state of the pore water vapor, which is assumed equal to that of the pore water. And so it relies on that thermodynamic equation. Temperature is very important. These are essentially constants, but that temperature is controlled very precisely in the device. What's nice about this device is it's very rapid. It has to come to equilibrium. It has to get the temperature to an equilibrium state before it makes the reading. So for clay soil, it may take up to 15 minutes, but that's pretty quick in terms of measuring suction. So you can take samples, in situ samples that have been preserved from the field, and you can measure total suctions. Of course, the drawback is that it's total suction. It doesn't consider the osmotic component, the salt content that's in that soil. Another method that can be used is the filter paper method. And here there's two approaches you can use. One is called contact, one is non-contact. And so in the non-contact method, you don't let the filter paper come in contact with the soil. And so what happens is the moisture content in that paper comes to equilibrium with the moisture content of the soil, given there's enough time. So these take quite a bit of time, probably week or more to get equilibrium in that filter paper. And then the contact method, you take that filter paper and you sandwich it between two sacrificial filter papers, sandwich it between the soil, and that measures matrix suction because it allows the water to migrate, so you also get an equilibrium in salt concentration between the two. And then you use this calibration between filter paper water content and suction to get your suction values. So this is an inexpensive method. It does take extreme care and it takes time. You have to control the temperature very precisely, but it has been widely used. I think Jim Nevels has a lot of experience with this test, and he can attest to how sensitive it is. I mean, because you're measuring extremely small weights. You need a scale that measures to a 10,000th of a gram. So everything has to be carefully done. No contamination on the papers. It needs to be done extremely carefully. Okay, so what about the osmotic suction? So there are ways you can measure or estimate this. One way would be to use the filter paper method, contact and non-contact, and take the difference between the total and the matrix, and that will give you the osmotic component. There is a method called the pore fluid extract method, where you basically squeeze the pore fluid out of a soil sample, this device here, and then you measure the osmotic component of that water. You measure essentially the molality, which you can relate to the osmotic suction. Another method that was developed in my lab by a visiting scholar and myself is to actually use the WP4 to estimate osmotic suction. And the graphs over on the right are from that research. And what you'll notice, these are plots of water mixed with salt and then mixed with different soil types. So we have points for the pure solution. We have points for the solution mixed with bentonite, kaolinite, and sand. And then we measured the osmotic suction using the WP4 in each of those mixes. And this was in a saturated state. So there's no air, there's no matrix component in these measurements. And what you notice is that there's virtually no difference. Right? So what that means, since the osmotic suction of the pure solution is the true osmotic suction, and it's the same whether you mix soil into that saturated solution or not, you can take your field sample, do your measurement, your total suction measurement in the lab at the natural water content. So then you have natural water content, you have total suction for the field sample. You then take that sample or some representative portion of it, you mix it with water till it's thoroughly saturated, and then you measure the suction again. Well, this time you're measuring osmotic suction only because you've saturated the sample, you've gotten rid of the matrix component. Problem is you've diluted the salt concentration, so you've changed the osmotic suction. But you can use this equation to calculate the osmotic suction of the field sample based on the water content of that saturated sample that you use to measure the osmotic component and the field water content. So it's a simple way to use that WP4 to measure osmotic suction. This B exponent basically describes the slope of these lines, which in many cases is 1, but there is some variation depending on the salt ion that's present. So in a sense, that would make it approximate because you'd either have to know what kind of salt species you have in that water or just assume a B value, okay? But those salts are what are frequently occurring in nature. There are others, but those are very common. All right, any questions? Okay, I think, let me see what we got left. We're going to take a short break. Yeah, let's take a short break. 5 minutes. And that way, if you want to get some coffee or food, we'll reconvene at 9:08:23.
right. You get a point there. You got all points of the spectrum. You go just to these, yeah, you go just to these, it's not easy. That's right.
All right, so we'll get started again here. You guys can hear me okay on the Teams?
Yes, sir.
All right. Looks like we're good. Yeah, so as I already mentioned, and I'm not going to go into great detail. Oh, something didn't go right here. Hold on. I lost my screen for some reason. Oh, there it is. Okay, that's back. Okay, as I mentioned earlier in my presentation, that it's important to think about the difference between total and osmotic suction, because really it's the matrix suction that has the greatest effect. It's not that osmotic suction doesn't influence behavior. It's just that its influence is generally not as important as the matrix suction. So often we're interested in looking at the matrix suction. And so if we're making these total suction measurements, we need to think about that. And just to illustrate the point, there's a couple of figures here from the literature that show how osmotic suction, pointer doesn't work, how osmotic suction varies relative to matrix suction in a soil and total suction. And so you can see for this range of water content, there's very little change in osmotic suction over that range of water content. So the influence of that osmotic suction is going to be minimal because it doesn't change much. But yet the matrix suction changes significantly over that same range of water content. These figures over here are from Nelson and Miller. And this is a really good paper that talks about the importance or lack of importance of osmotic suction on behavior. And so you got two plots, one with matrix suction, one with total suction. So these are shrinkage compression curves for soils that were compacted dry and wet of optimum at different salt contents. Up here, you can see, and these curves up here represent all of the salt contents. You can see that if we look at it in terms of matrix suction, the salt content has very little influence on behavior, because all of these salt contents are represented and all the points plot on the same compression curves for dry and wet of optimum. But if you parse it out based on total suction, you would conclude that there's a big difference due to the salt content. But that's just because the salt content is affecting the total suction measurement. It's not really affecting the mechanical behavior. So again, it's important to be thinking about that osmotic suction when you're making total suction measurements. We often use total suction as a surrogate for matrix suction. And that can be reasonable, but what I found in my own experience is when you're testing unsaturated soils that are in kind of a wetter state where the suctions, you're approaching that saturated condition, the difference, it makes a big difference. Because again, even in a saturated soil, osmotic suction will be present. Okay, another way that you can estimate the soil water characteristic curve is to use an empirical approach. And I have come to really depend on this method of Zapata et al. Because it works pretty good. I've done a lot of comparisons with this soil water characteristic curve, empirically determined actual measurements, and generally it's pretty good. So why it's useful if you don't have any way to measure suction or to determine the soil water characteristic curve, you can estimate it empirically based on, for a cohesive soil, the plasticity index and percent of fines, which we all measure in the laboratory on our samples. Or for a granular soil, a cohesionless soil, you use the D60, the diameter corresponding to 60% passing. And then using those parameters, you come up with the fitting parameters for the soil water characteristic curve. So this function proposed by Friedland and Zing is just it's a curve fitting technique that happens to work very well for, creating soil water characteristic curves. So using the Zapata method to estimate the fitting parameters, and you can also estimate the saturated volumetric water content if you don't have that, you can plug these values in this equation and you can generate a soil water characteristic curve. Very simply, you just have to set up a spreadsheet to solve those two equations. And you plug in your PI and your percent of fines and you generate a curve. And so here are some that I've generated for different soil types. And those are the equations, by the way, for those fitting parameters. That paper, again, is Zapata et al. 2000. And by the way, if you're interested in any of these papers, just let Olivia know or let myself know, and I'll be happy to send you some, the ones that I have. Okay. But I use these and I just varied the PI and the percent of fines and generated that series of curves. And you can see that the high PI clay gives you the largest range of suction. And then down to the largest sand particles, you get very low suctions. And these are megapascals. So but you can see that the suction range for a coarse granular sand is really quite small. That's why in these cohesionless coarse grain soils, the suction does not play as significant a role. It still will affect your test results, your in situ test results. And so you still want to think about it, but the effect is not nearly as significant as it is in a clay soil where that suction can get very high. All right, so the last part of the background part of my presentation deals with stress state variables for unsaturated soil. And so to get, excuse me, to get us started, we're going to talk about saturated soil. This is what we were all, at least the geotechnical engineers, I know some of you are not, we were all trained, but if you're a civil engineer, you took a soil mechanics class probably at one point, and you learned saturated soil mechanics for the most part. So in the saturated soil, it's been pretty well established that the Terzaghi effective stress equation describes the stress state appropriately and can be used to estimate mechanical behavior using constitutive relations involving that effective stress variable. And so it is the total stress. So here's an element of soil. You can think of this element of soil somewhere below the ground surface, below the water table. We've got a overburden stress, a total stress, which is due to the weight of soil and water above this element. And then we have pore water pressure acting everywhere within this system. And so basically, the pore water pressure tends to reduce the intergranular contact stress, right? So that we have this weight acting down, which is tending to push particles together, creating these contact stresses. But then we've got this water pressure that's trying to push particles apart, essentially, or kind of like a buoyant force, actually. And that's reducing the interparticle contact stress. Well, if you think about soil behavior, shearing resistance, for example, or compressibility, if I try to shear this mass, in order for the particles to move and shear, we have to overcome the frictional resistance at these contacts. The higher that normal stress between those contacts, the higher that contact stress, the higher the frictional resistance. So it makes sense that that effective stress, which describes essentially these contact stresses averaged over some engineering area, essentially that's what effective stress is, right? It's a measurement of contact stress averaged over a larger area, that engineering area. So as these increase relative to increasing effective stress, we get more shearing resistance. As they decrease, we get less shearing resistance. So for example, our strength equation says that the shear strength, and this is our Moore Coulomb failure criterion, says that the shear strength is equal to the effective stress times some tan phi, that's that coefficient of friction essentially, plus C prime, which is a stress independent component of strength. So that would be due to cohesion or cementation or something like that. So it makes sense that this effective stress describes behavior very well because it's a measure of that contact risk. Same with compressibility. You have a higher effective stress state, you have a stiffer soil because it's harder to move particles that have high contact stresses between them. Again, particles have to move for soil to experience volume change. And so you're going to have to overcome the stresses at those contacts to get soil to move. So generally, these same principles, at least in terms of, the idea of inner particle stress controlling behavior, it's the same for unsaturated soils. It's just that the way they develop is different because now we have air in there. So we have to consider how the presence of air and the interaction of air and water affects those inner particle stresses. So for saturated soils, a single effective stress variable is generally sufficient, and that's the Terzaghi effective stress. And that single stress state variable is just total stress minus pore water pressure because the soil is saturated. There's no air. We don't have to consider how the air affects that behavior. But in saturated soils, we have this air phase. And as a result of that and the interaction of the air and the water, we now have this matrix suction. So we have to consider the matrix suction, the difference between UA and UW, in our description of effective stress. And so two general approaches are out there. There's actually many, many different equations that have been proposed to describe effective stress. Often they boil down into these two, I call it Bishop's effective stress approach, which would incorporate a large number of the models that are out there, and then the two stress state variable approach. And so I'm just going to briefly explain each of these approaches. So the Bishop's effective stress approach defines effective stress as shown there. So it accounts for the presence of the air phase and the matrix suction that develops because of that. And so it's what we call the net normal stress, the difference between total stress and air pressure, again, which is often zero. And then plus that additional term due to the suction. So we've got effective stress that results from the normal stress. Again, that's the overburden stress, weight of soil and solids with soil and water above that point. And then we have this component that's contributed by the suction. So we've incorporated the air phase, the pressure in the air phase into our description. And then you have this term chi, that's sometimes referred to as the Bishop's chi. In a sense, what that does is describes the interfacial area between the water and the solid phase. Right, so think of it this way. You've got this soil suction acting between these particles. That's a pressure, right? It acts over a certain area, which is essentially defined by the distance between those menisci in this photo. So that essentially is a representation of that solid liquid interfacial area. And so as the degree of saturation decreases, the suction goes up, but the chi goes down. In fact, chi has been proposed to be equal to the degree of saturation. So in a low degree of saturation, your chi is small, like 10% saturation, 0.1. But your suction is very high. But the contribution of that suction is diminished because the interfacial area is smaller. The area that this water phase acts over gets smaller and smaller and smaller. So chi kind of helps to describe that interaction. That make sense? Okay. And so the nice thing about Bishop's effective stress approach is that generally you can import this effective stress description into models that we use for saturated soils and describe strength and compressibility in terms of that single valued effective stress given by that equation. The other approach is to use two stress state variables and basically treat the net normal stress, which is the difference between total stress and air pressure, and the matrix suction, UA and UW, independently. So to consider their contributions independently, and so now you have two stress state variables. And that means then for each stress state variable, in terms of the shear strength equation, you have a coefficient associated with that stress state variable, and you have one associated with that stress state variable. Well, when it boils down to shear strength, these two methods are quite similar. And in fact, I've sort of summarized at the bottom the similarity. If you were to equate those two equations, what you end up with is essentially that chi times the tangent phi prime is equal to tan phi b. So that phi b in the two stress state variable approaches can actually be related back to the Bishop approach. But there are other behaviors such as volume change behavior that may be better described by the two stress state variable approach, but we're not going to go into that today. And so this is just a summary of a comparison of these stress state variable approaches using shear strength as our reference. And so one thing we note that this is kind of an interesting behavior, this tan phi b is often nonlinear, a nonlinear function of suction. So whereas phi prime is usually linear over a fairly large range of normal stress, phi b tends to change with increasing suction. And again, that relates back to this changing of the interfacial area. The suction becomes less effective in the soil as it increases because the solid liquid interfacial area is getting smaller. So you get a nonlinear effect because of that. And then it gives you a nonlinear strength envelope. Stress state variables are direct. This is one thing I like about the two stress state variable approach. You can relate these two stress state variables to readily measured quantities or quantities you can control. So in the laboratory, if you're doing unsaturated soil testing, you can control total stress, say cell pressure in a triaxial test. You can control pore water pressure, just the way we do it in a triaxial test. And you can control air pressure if you have the equipment set up to do that. And it's out there, and you can control air pressure. So what that means is as you're running the test, you can plan your stress path in terms of net normal stress, sigma minus UA and UA minus UW, and you can follow it very easily and see the soil response. The Bishop approach, though, involves this chi term, which is related to degree of saturation. Well, you may not know how the degree of saturation is going to change during your testing, so you really can't control this stress state variable, that Bishop effective stress, during your lab testing, because you don't know what the degree of saturation is. I mean, you might know where it starts and you can estimate it, but in terms of controlling a lab test, this is a little more intuitively pleasing. Okay, so that's just a brief overview of the comparison of the two stress state variable approach and the Bishop approach. Actually, so if we were to compare the shear strength measurements using those two approaches, for the two stress state variable approach, you would end up with a different Mohr Coulomb envelope for each level of suction. And in fact, you could plot this information in a three-dimensional space with net normal stress, which is your mean stress, deviatoric stress, which is your shear stress, and then you could have a suction axis, and you'd see a plane that represents these different failure envelopes as a function of different suctions. Nice thing about the Bishop approach is they all collapse onto a single failure envelope. Okay. So the differences are, they're really not that significant in terms of shear strength. But again, this one utilizes the chi term. This one uses the independent stress state variable approach with tan phi b describing the change in strength with suction. And so in terms of defining phi b or chi, this is just an example of chi versus degree of saturation. You can see that generally these curves are close to 1, the relationship. In other words, coefficient is equal to degree of saturation along there. But some research has observed that if you back calculate that chi, it actually varies a little bit from the degree of saturation. And then this is what the tangent phi b looks like. So you'll notice that it starts out quite linear and then it becomes nonlinear. So that is a challenge. If you want to use a nonlinear representation of phi b, you have to have some way to describe that. What do you think happens where it changes? What do you think is going on? So think of it this way. We're increasing suction in this direction, and we're decreasing water content. So what's happening when we transition here from linear to nonlinear? Think about that soil water characteristic curve. Remember when it starts out? Initially, water content doesn't change. Essentially, the soil is behaving like a fully saturated soil. And in fact, that initial slope is often equal to phi prime. And then it starts to become nonlinear once the soil desaturates. Okay, so that is the background information. And now we're going to jump into some practical applications of some of this information we just discussed. Before I do, is there any questions? Do we have questions? Olivia, do we have any questions? Okay. Okay, so first thing we're going to talk about is interpretation of standard penetration test. I think this is probably something of interest to a lot of folks in practice because we rely heavily on this test. And again, just to refresh your memory, our concern is, if depending on when we run our SPT or standard penetration test, and the conditions of the soil, whether it's in an unsaturated or saturated state, we're going to get different results. Now, of course, the main concern is if we run the test during a dry season and we use that to estimate strength and compressibility, how's that going to change if the soil becomes wet? And so in my example, we'll just look at bearing capacity, but we should be using the same thought process to think about settlement. How's the settlement behavior going to change if the water content changes? So then I pose the question, how do we address this quandary? So what can we do to address this? We've got this issue. We need to somehow get a handle on how SPT might change with water content and then implement that in our approach to design or analysis. So I sort of broke it down into 3 steps here. First thing we have to do is understand the importance. How much of an effect does it have? If that water content changes, what is the influence going to be? And so for that, I'm just going to show you some data that we've collected, but there's not a ton of data out there. However, I'm going to suggest that you probably have a lot of data in your company records that you could use to start looking at this. Second, we must assess how the expected changes in N values will affect the estimated soil properties for design. So Once we know the impact of moisture content on SPT, we can then do some what if scenarios. You know, what if the site becomes completely saturated? Or what if the moisture content increases this much? How's that going to affect my N value? Okay. And then after that, how's it going to affect the estimated soil properties? So if I'm using N values to estimate total stress strength of clays, which is not highly recommended, but sometimes done, or I use it to estimate modulus of elasticity of soils or friction angle of sands, how's that going to change if the moisture content changes and that N value changes? And then finally, how's that moisture-induced change in soil property going to affect the performance of our structures or the recommendations we give with respect to bearing capacity and settlement? So we're going to look at these three items. First, we'll talk about the impact of moisture content and suction on SPT N values. And so I'm going to start by showing you data from a couple of test sites where we've done a fair amount of work. And the first is what we call the Goldsby site, which is basically down off of I-35 near Goldsby, just so you have a sense of the soil profile that we were dealing with. So this was a soil profile consisting of medium to low plasticity silt and clay, most of it classified as CL, and had about 5 to 25% sand. And so you can see the soil properties here, the classifications. We did have sort of when we analyzed this, we kind of broke it into two layers because there was sort of a marked increase in sand content below this depth, which seemed to affect the behavior. And then there was also sort of a shift in PI. The average PI in the upper layer was lower than in this, higher than in the lower layer. And then you see the variation of degree of saturation from different dates when we tested, and then estimated dry density. So this was the first site. The second site had higher PI soils. This was called the North Base site, which is up there by Max Westheimer over towards more to the east. And that's a fairly high PI soil area. And so at this site, soils range from CL to CH. PIs tended to be on higher. And again, we broke it into different layers depending on the average soil characteristics. So here's your water content, the squares on a couple of dates, liquid limits and plastic limits. And again, degrees of saturation varied during the study. So these are the two study sites. So what we did is we went out to these sites, and I can't remember how many visits. We had at least a half a dozen, maybe more, over a period of 2 years. So we had changing weather conditions, seasonal variations in moisture, and we ran in situ tests. We ran standard penetration tests. We ran cone penetration tests. We actually ran pressure meter tests as well, but I didn't include those in today's discussion because I don't think the pressure meter around here is used that frequently in the soil profile. Do any of you use pressure meter in the soil? Mainly in the rock, so I didn't include that in this discussion. And so each time we went out, we would do these in triplicate, and then what I'm going to show is average profiles. So the first plot is a result from the Goldsby test site. Again, these are average SPTN values. Now I only picked 2 dates, so I picked the wettest and the driest date to show you the extreme difference. This is over a period of 2 years. And so here's the variation in average SPTN values. There's the variation in water content. So each time we went out, we also took samples, did natural water content determinations, and we measured total suction and estimated matrix suction. So you can see that there is a pretty significant difference and the SPTN values in the upper 8 feet of this soil profile. Which means that if you ran your tests during the drier period, you'd be thinking, hey, that's pretty good clay. It's pretty strong clay, but you start getting down SPTN values of 4, you might rethink putting spread footings on that. So again, here's an example of how that difference can manifest itself in terms of your SPTN values. And then our North Bay site, the differences were even more significant. And again, it's probably because higher clay content, higher suctions, more effect due to wetting and drying. And so average SPTs were quite high during the drier period. During the wetting period, again, not that high. So big difference. And the variation in moisture content is pretty significant on these 2 dates. Anywhere from 8 to more than 10% difference. So, but the difference is, it's interesting. If you look at the variations in water content, it looks like below about 6 feet, the change is relatively minimal, but yet you still see a difference in the SPTN values. And this could be related to that hysteresis effect in terms of wetting and drying matrix suction. So in other words, the suction that we measured on that particular date may actually be higher than indicated by this plot. So the wetting and drying does seem to affect to a depth that's greater than water content variations might suggest. Okay, so now you have some idea of how much change can occur. But I think this next slide may be of particular interest to you. So I took 10 test sites, just random projects. Actually, I want to give a shout out to Medco for providing this data. And I just started going through test borings, taking N values and water contents and seeing if there was any correlation. And I parsed it out by different soil types. And while there is significant scatter in the data set, and I expected this because in natural soil profiles, you often see significant scatter because there's a lot of other variables besides water content that are going to affect SPTN value. I also converted this to N160 because a lot of available correlations are based on N60 or N160. But the reason I'm using N160, if you remember, N60 is SPT corrected for hammer efficiency. Most of our automatic hammers are going to be 75% or so. Whereas a lot of the correlations were developed when rope and cathead was around. And back then, we were probably closer to N60. So I adjusted the energy. If I didn't, the correlations would still work. But I also corrected based on the depth of the test and the overburden pressure, which is where the N160 comes in. So this N160 is N60 corrected for overburden pressure because N is going to vary with depth simply because of changing overburden pressure. So I want to compare apples and apples. But these correlations are not terrible. I mean, the coefficients of determination are generally low. That one, I would say, is pretty darn good. That's for that CH soil. But this is just 10 sites randomly taken. I didn't go through and pick sites. I just got 10 test sites. And well, so you can do this. You can look at your archives, your test borings, and you can create a database of water content versus N value. And I would recommend using corrected N value. You don't necessarily have to do 60, but you want to correct for overburn or normalize by overburn pressure. And you can begin to maybe see some of these trends. So this, in a sense, can be used to estimate how SPT might change as a function of water content. And I'm going to show you an example of how I use it. Okay. Any questions? Yeah, Ollie.
Yeah, if you go close to the surface, you can see a significant difference between two different dates in matrix structure and water content.
Mm-hmm.
But the difference is very low for a split number. Makes sense?
It doesn't necessarily make sense, but that's what the data says. I attribute that probably just to the natural variation in the soil. You know, you're averaging water contents from 3 different samples. You're averaging N values. Probably if we looked at each of the SPT profiles separately, it might make more sense. I know what you're saying. There's a big difference in water content up here, but that's not reflected here. But you also note that this point is quite a bit higher than this point. Well, it's a half a foot, but a lot can happen in the half a foot, right? Because at the ground surface, that's where the exchange in moisture is occurring. So if you had a significant rainfall event, you know, it could cause significant wetting down to this depth, but maybe not get down to this depth. So yeah, it's a good question. I don't have a great answer, but that's probably has to do with those natural variations. Okay, so then the question is, how does this affect the estimated soil properties used for design? So first, I'm going to just use it to estimate undrained shear strength. And again, using SPT to estimate undrained strength is not ideal, but often it's the only measure of strength we have for a project. I'm sure many of you have had projects where all you have is SPT and soil properties. So if that's all I have, I'm going to use it, and keeping in mind that its use is there's a lot of uncertainty with it. The other thing is the concept of undrained strength is not necessarily applicable to unsaturated soils. Although we use the undrained strength based approach or the total stress approach to estimate bearing capacity based on this undrained strength, I like to refer to it as a total stress strength. I think it makes more sense. But in any case, let's see what happens to this estimated undrained shear strength if we use a correlation to estimate it. So I looked at 2 correlations. I'm not sure what you guys would use to do this. There's a lot of different correlations in the literature. This first one is Herodol 74. It's actually based on Japanese clays with relatively low OCRs. So maybe not terribly applicable to our clays, which tend to be more over consolidated. And then in this equation, we have N60. Again, that's the penetration resistance corrected for hammer efficiency. I assume 75% for the automatic hammers that we were using. And then atmospheric pressure is the other term in this equation, and here it is given in various units. The other correlation I looked at was from Peck, Hansen, and Thornburn. This is, and actually the correlation, they don't have the correlation published, but they have this essentially comparison between clays of different unconfined strength compared to a range of SPTN values. So I took those ranges and I converted unconfined strength to undrained shear strength, which is just 1/2 the unconfined strength. And I plotted that versus the SPTN values. And so that's the correlation I got. So undrained strength is 133 times N. Now they don't call it N60, but I'm assuming back in those days, again, it was probably mostly rope and cathead, not automatic hammers, because that was before my time. And when I started practicing in engineering consulting back in late 80s, early 90s, all I saw was rope and cathead. So I'm assuming before then it was probably all rope and cathead. And so I'm assuming the efficiency was probably N60 for that correlation. So then what I did is I compared those two. So the orange is that Herodol equation based on N60. This blue line is the Peckadol equation. And so I just averaged the two and fit a little power equation to that. And so this is what I got for estimating undrained strength based on the average of those two correlations. So that's what I'm using in my example. So then I can simply take that and apply that to my SPT N60 values. So convert my SPT values to N60 values and then estimate undrained strength as a function of depth. And so, it varies from a minimum during the wet date of around 1,000, which is not terribly strong, to close to 3,000 for the greatest on the drying depth. And so what I did for my little demonstration, next I'm going to analyze bearing capacity using a total stress approach and undrained strength, or total stress strength. And to do that, I assumed that the zone of influence for bearing capacity was the entire profile. So I averaged these over the entire profile to do my comparative analysis. So the average undrained strength was 2526 for the dry date, and then for the wet date, 1907. Now, if I was real conservative, I would have just looked at the upper 6 feet. The difference would have been larger. And then I did the same thing for north base. So again, on the left, you see SPT N60s for the two dates, the dry date and the wet date, and then the corresponding estimates of undrained strength. And here the maximum, the difference between the minimum and the maximum is much larger, and the difference in then the averages is much, much different. Again, this is over the full profile. So that would be the difference in undrained strength. And just looking at that, factor of safety is roughly proportional to undrained strength. It's almost a factor of 2 in terms of your factor of safety. And then the other example problem, I'm going to use, I'm going to assume a sand material, and I'm going to use N160 to estimate the friction angle. So I'm using an equation from Bowles. I'm a big fan of Mr. Bowles. I love his books and his insight. There's a lot of different equations out there. I just picked this one. Normally, when I approach these problems, I'll use 3 or 4 different correlations and just see what I'm getting for a range. But for this example, I picked this equation from Bowles, and I adjusted it from N170 to N160 because that's what I computed for my values. So this is the friction angle of the sand. Again, that's used to estimate shear strength of sands. And then also I decided to look at the modulus of elasticity based on N values. And so this is a correlation from Main and Kalhowie based on N60 for sands. And so there's a big range in what you can predict with this equation. So this alpha value has a huge influence on the estimated modulus of elasticity. It's 5, 10, or 15 for silty sand, clean sand, or over-consolidated sand. Okay, and then this is just a definition of the terms in these equations. So here's that equation for N160. It's N160 is N60 times the CN factor, and I'm using the CN proposed by Lau and Whitman, and again, it incorporates the vertical overburden pressure or effective stress at that depth. And then we have our atmospheric pressure. So for this example, what I'm doing is, and so this is just a hypothetical scenario. I'm assuming that in the upper 10 feet of my sand, on the day of my investigation, I had an average SPT N160 of 37. And on that day, the average water content corresponding to that was about 15%. And the soil was in an unsaturated state, and this is what I would consider a dry period. So my question is, how is the friction angle and modulus of elasticity going to change if the water content increases prior to constructing my footing? And so I'm going to use my empirical data that I showed you previously to show how I'm going to do that. And I'll show you how my approach. Okay, so To do this analysis, I'm interested in knowing what happens if the soil becomes near saturated. You know, what happens if that water content increases to near saturation, which is about 22%. So I'm going to analyze my change due to an increase from 15 to 22%, or basically a change in water content of 7%. And so to do that, I'm going to use the curve that I developed from my database for the sandy materials. And so that would be my orange curve here. So I'm going to use this equation, which is a best fit line for that set of data, to estimate how my N160 is going to change. And so first I just took my water contents, 15% and 22%, plugged them into my equation. You'll notice the exponent here is W, water content, in percent. So I plugged that in, and these are the N160s I get based on that equation. Well, at 15%, I'm not at 28.8, but what I'm going to do is assume the change of 7% is that slope is going to be the same, whether I start at 37 or I start at 28. So in other words, basically I just computed these values, and now to get my estimated SPT N160 based on my numbers, I have, remember mine's 37, it's not 28, but I'm going to assume the difference is the same. It changed by 11. So my new N160 at 22% is going to be 26. And so what that looks like, so basically I'm just starting up here with my point, and I'm following that curve, following the slope, and that's where I end up. So the delta is the same, just I start here instead of here. You follow? Okay, so now I have my new N160, and now I can estimate how that impacts my modulus of elasticity and my friction angle. And so there's a summary of those results. So my dry condition with N160, remember that's the average in my zone of interest for my footing analysis, gives me a friction angle of 34.4 degrees, whereas my wet condition gives me a friction angle of 30.1. And that's actually quite a difference. And if I look at the modulus of elasticity, now for modulus of elasticity, it depends on N60, not N160. So what I did is just calculate the average, this CN factor for the average over the depth, which was 10 feet, and used it to calculate N60. So I just kind of did it in reverse. And then I use these N60 values to estimate modulus of elasticity, and it goes from 378 to 270. Okay, so let's pause there. So basically, I just showed you a simple approach for estimating how your SPTN values might change with a change in water content. Now, this is highly empirical, and there is uncertainty, but I would argue that not considering how it's going to change is probably worse than using some empirical approach to come up with a reduced SPTN value for your analysis. Make sense? Questions? You think you can develop these curves back in your own offices? Yeah, I know, it's a lot of extra time. Yeah, I've been lucky to have Metco provide me a lot of data, so I've been able to develop these curves. But it is time consuming. You sit there and look at borings and pull off water contents and values, but you probably have all that digitized. You may have it in tables somewhere. It wouldn't take long to put that data together and you can start developing some of these. And again, they're empirical. There's a lot of scatter, but you should expect scatter because N value does not only depend on water content. It depends on the density. It depends on the stress history. It depends on the nature of the particulate material, the mineralogy. So there's a lot of factors that aren't considered in this. Nevertheless, the trends are not horrible and they're in the right direction. So it gives us some sense of how those N values may change as water content changes. And note that some of these points actually represent saturated conditions. So most are unsaturated. Okay, so the last step in this process then is to see what effect these changes in estimated soil properties have on our analysis. And so I'm going to start with a bearing capacity example for clay. And so I'm assuming a square footing, 2 foot embedment, 5 by 5, a unit weight of 120. Obviously water tables below this. This is the unsaturated zone. And again, I'm assuming actually that 10 foot should go up to the surface, 10 feet of influence depth. Basically the extent of my data that I had from the two sites. There's my bearing capacity equation. So in this equation, this is the general bearing capacity equation. This is the Terzaghi equation for a square footing. So we have a shape factor of 1.3, a bearing capacity factor. And if we do a total stress analysis and assume the total stress friction angle is 0, then the C term becomes equal to the undrained shear strength or the total stress strength. And then our bearing capacity parameters are such. So the equation basically reduces to, I left out a C. It should be 7.4 CUNC plus gamma 1 D sub F. So that's what I'm using. And again, these are the two profiles I'm comparing. Same site, different dates. And so this is what the analysis looks like. And so if I was to use these equations and those average undrained strengths on the wet date, my ultimate bearing capacity would be 14,354. This is at Goldsby versus 18,930. With a factor of safety of 3, these would be my allowables. I know these are quite a bit higher than most of us would give, but this is what the numbers show. And then what this means is this is what we might give the client. Now, I know most of you probably wouldn't give 6,300, even though the data supports this. There's other considerations like settlement that we're not looking at. Nevertheless, this might be the actual that we would recommend based on the allowable. Now, if we did this during the dry season, we'd be saying, okay, 6,300, hypothetically. But what happens if we get significant wetting before they build that footing and our undrained strength actually drops? And we still have given 6310. That means the factor of safety, the actual is still 6310 over, even though the allowable should be 4785. Factor of safety would drop to 2.3. You follow? And then at North Base, again, if we base it on dry season, allowable would be 6552 for those numbers. And again, that's factor of safety 3. But if there's a significant wetting event before construction and shear strength decreases, our factor of safety for that actual would drop to 1.5. Okay. Now, we don't often get in trouble with this because typically our recommended allowables are so low that we never approach shear failure. And oftentimes settlement considerations control instead of bearing capacity. But this example does demonstrate that changes in N values due to changes in moisture contents can have a profound effect on the results of your analysis. And then what does that mean if you have significant wetting after that subsurface exploration? The other thing, and we may talk about this in the part 2 course, that wetting also affects the settlement behavior. And if these footings are on a compacted fill and you get significant wetting, you can have significant wetting induced compression. And that may be more of an issue than stability. Again, because we often give such low allowable bearing pressures. Questions? Okay, we'll look at my next example, and then we're going to take another 5-minute break, because it will have been an hour since we reconvened. I think we're staying on track pretty well. So the other example I talked about was looking at the sand case. So assume we have a silty sand. I want to look at, I have a friction angle, so I want to look at bearing capacity, and I want to look at settlement. So I picked a couple methods from the literature. The bearing capacity equation, in this case, I'm using the general bearing capacity equation, which is just, there's Augie's equation on steroids with a few modifications for various things. So in here you have a shape factor, depth factor, inclination factor. Those are all one. I'm looking at vertical axial loading. But I'm using this equation. And the reason I'm doing that is because I have a real slick spreadsheet set up where I can just plug things in and do the analysis. So I didn't have to sit there and do it by hand. And then for settlement, I'm using Main and Poulos approach, which I actually like a lot because it's a very flexible method. It actually considers the depth to an incompressible stratum, which I'm assuming is very deep in this case. It considers the variation of modulus of elasticity with depth. I'm assuming it's roughly constant, but the solution method will not allow you to put a slope of 0 in here. So I use something very, very small, like 0.001, just to get a number that I could use. So, but I'm using this, and then, so I'm essentially going to use a constant modulus of elasticity. These are how you come up with these influence factors for, IG is for the variation of soil modulus with depth. IF is the rigidity factor, so it actually accounts for the stiffness of the footing. And then IE is the embedment correction. But I'm not going to go into details on how to use this, but this is what I use to estimate settlement. And again, the main thing we're interested in is what's the influence of that, E0. Okay, so here's my scenario. We are increasing from 7% moisture content, which corresponded to our N160 of 37 during the dry period. We're increasing to 22%, which means we have significant wetting. And then I'm going to use the N160 corresponding to that. And we're going to look at how, and we looked at how it affects modulus and friction angle. And now we're going to look at what effect it has on bearing capacity and settlement. So I just put the summary of results here. And actually, yeah, I'll have to go back and look. Trying to remember what actual bearing pressure I used. I think I used the actual, but yeah, I'm almost certain I did. But anyways, this is how we estimated change in N160 using our empirical correlation for the sandy materials. That's our N60. There's our feet prime. So I evaluated bearing capacity with these two values, and I evaluated settlement. And so first, bearing capacity, there's the difference in bearing capacity. And so again, if you were to design based on the dry condition and give an allowable of 7223, and then you got wetting, essentially, you'd be using the same actual because that's what you recommended for the dry period. Your factor of safety would go from 3 to 1.8. And the settlement was not as significantly affected. It went from 0.9 to 1.2, which is borderline in both cases. So again, There is a significant difference in the N values depending on moisture content, and there's implications for that in terms of our analysis. So the main thing is, to be thinking about that. If you know you're out there testing during a drought, you should have it in your mind that, these clays are going to look very stiff. They're going to look very strong. Could be different if you were out there during a wet season. Any questions? All right. So next, we're going to spend a little time looking at CPT results. I know more and more of you are using cone penetration tests. I think it's an awesome test for a lot of reasons. But again, in that unsaturated profile, those results are going to be impacted by the water content and the state of suction. And so we'll look at that next. So let's take 5 minutes. I have 10:12, so be back here and seated by about 10:17. Sound good? Coffee? Treats? Okay, we're gonna go ahead and get started here, guys, if you wanna grab a seat. All right, so now we're going to look at some cone penetration testing. And again, the idea is the same. If we're running CPTs, we need to be thinking about what are the moisture conditions like in our upper soil profile in that active zone when we're out there doing the testing, and how does that relate to our analysis if the moisture content changes. And just to give you an example of how extreme, and I've actually got some data later to show you on this, how extreme the changes can be. Not far from here is our FEAR Structural Engineering Lab. And for my entire career, which started in '94, we've been doing a field testing class out there, laboratory and in situ testing. And we've been doing a lot of in situ tests, a lot of sampling out there. In the years that I taught that course, the water table was often below 15 feet. It seemed to like to be fairly deep, had that unsaturated profile, but during a few years, it actually rose to near the ground surface. Now, that's a pretty extreme change in the saturation state of a soil profile. So these changes do occur just depending on where you are and what the ground cover conditions are like and things of that. So, all right, and so we're going to use the same approach. First, we want to look at, we want to understand how significant these changes can be. So we're going to look at some data that I've collected as well as others that relate tip resistance to moisture content or suction. And then we're going to look at how expected changes in QC and FS due to changes in moisture content affect our estimate of soil properties, and then how those changes in soil properties may affect our analysis of various, geotechnical structures. But keep in mind, I'm just looking at a footing and bearing capacity, but you can apply this approach to any problem, whether it's looking at slope stability in particular. I'd argue that most of our slope failures probably occur in an unsaturated state. So if you're trying to do a forensic analysis and you're using saturated strength parameters, it may not be terribly precise. But if you look at variations in moisture and how that affects shear strength, generally slope failures occur due to wetting and significant wetting, but they may be triggered prior to reaching a saturated state. So whether it's slopes or footings or pavements or whatever, you need to think about how changes in moisture content are going to affect our analysis, and then how the interpreted soil properties based on our in situ tests are going to affect our analysis. All right, so I think most of you are familiar with the cone. So basically, you push a instrumented cone, typically stainless steel, typically has a tip and a sleeve. Each of these are attached to some load cell. There's different load cell configurations. They could be independent load cells, or it's a subtraction cone. They measure both, and there's another load cell that measures the difference. But in any case, from these load cell measurements, we can get the force acting on the tip of the cone, the force acting over the sleeve, divide those by their respective areas, and get the tip resistance, which has units of stress, and the sleeve friction, which also has units of stress. And those two measurements are very useful for estimating soil properties and for soil classification. So you can take a combination of the tip resistance and what's called the friction ratio, which is the ratio of the sleeve friction to the tip resistance expressed as a percentage. And those two parameters can give you a very good idea of soil type. And the idea being basically that sands tend to have large tip resistances, but low friction ratios, whereas clays tend to have relatively lower tip resistances and high friction ratios. So just looking at a plot of friction ratio versus depth, you can say, oh yeah, that's probably sand, that's probably clay, and there's various obviously in betweens. The classification schemes that are out there, you can parse the soil types into pretty fine detail, like 9 different categories or something like that. But it is useful. So it's a good profiling tool, meaning that you can get soil type with depth. The other thing that I love about this particular test, well, there's more than one thing, but one is that it's relatively operator independent. So as long as you follow the standard, your equipment is calibrated well, you penetrate at 2 centimeters per second, you're going to get the same results, or you should, as the next guy running the test. Whereas the SPT tends to be highly operator dependent. It used to be more so when we had the old rope and cathead. And it is a dynamic test, which affects it. So the SPT tends to be very consistent. The results are probably much more reliable in terms of repeatability. And there's a lot of different correlations, empirical correlations that can be used to estimate all kinds of soil properties. You can even directly estimate settlement, things like that. So it's a great tool, but just like the SPT, it's going to be affected by the moisture condition in that unsaturated soil profile. Now you'll notice I have not included the pore water pressure sensor on this particular diagram. And why do you think that is? Do you think that pore water pressure measurements in an in an unsaturated soil are going to be reliable? Probably not. It's not that they're useless, but you may recall, those of you who have worked with the what we call the piezo cone, which has the saturated porous element, in order for that piezo element to function properly, first of all, it has to be completely saturated, right? With some kind of fluid, silicone oil or glycerin or whatever you're using. Okay. And so that means that it really should only be used in saturated soils. Because what happens in an unsaturated soil, when you start pushing that cone into the ground, first of all, you tend to get significant dilation, which is a tendency for volume expansion right around the position of that porous element. That tends to create a negative pressure of suction, which actually pulls the pore fluid out of your sensor or can. Okay, once you get air inside that sensing element, you then get what's called hydrodynamic time lag, because the air is compressible. And so to transmit pressure to the pressure transducer, the diaphragm, every change in pressure out here has to go through that porous fluid and hit that diaphragm. Well, if there's an air bubble, that air bubble is compressible, so it has to adjust its size in response to a change in pressure, which means that by the time it adjusts its size, you're already down here. So the pressure you're measuring is not the pressure that was up here when you recorded it. So it's called hydrodynamic time lag. So that the variable compressibility of that fluid affects the measurements and how they correlate with depth. So I'm not saying it's not worthwhile. I'm just saying be careful in how you interpret pore pressure measurements in an unsaturated profile. What it is useful for, I still think there's some use to having it part of your exploration. When you hit the water table, you often will see it pick up and you can detect where the water table is. So but just be aware of that. Oh, I had something else on my mind I was going to say about that, and it just slipped away. It's been happening more and more since I turned 60. Yeah, maybe it'll come back to me. Oh yeah, I know what I was going to say. So I did a lot of this when I was a graduate student, a lot of piezo cone testing. And, I worked in New England in the Northeast, and the water tables were quite high. And so we would always pre-drill a hole to the water table, fill the hole with water, take the piezo cone out of, it always was in water. Once we desaturated it, it never lost contact with water or the fluid that we used to saturate the stone. And then we would lower it in the hole into the under the water, and then take off the protective cover that was holding the fluid in there. So it never saw air. That's how careful we were about keeping that pore stone saturated. So there's no question when you punch through an unsaturated profile, you're gonna remove fluid from your sensing element. Okay, I'm not going to talk about this again. We did this at the same two sites we did the SPTs at, and these were the results. So here I've plotted the here I just showing you all of the data from the different dates. So again, this was over roughly a 2-year period, and you see significant variation in tip resistance. This is actually friction ratio. I didn't plot sleeve friction. I just plotted friction ratio because really that's what I want that sleeve friction primarily for, is for classifying, profiling the soil. And a lot of variation there. And that variation tends to correspond to that large variation in moisture content and matrix suction that you see in the upper profile of the site. And here, the changes again, well, there seems to be still some activity going on below where the water content gets essentially constant. You tend to correlate a little stronger with the variations in water content. So that's Goldsby. And then this is the North Base CPT data. And again, you can see there's quite a bit of variation, and on the particularly dry dates, you do see a significant difference in tip resistance, which is typically used to estimate mechanical soil properties. And then also a difference in friction ratio. So you can misclassify soils based on cone penetration tests in the unsaturated profile, because for example, a very dry clay might behave more like a granular material in terms of frictional resistance than a wet clay. So you have to think about that as well. So the next slide, I'm going to show you a summary of all this work. There's a lot going on here, so I'll take a second to explain these figures. So in the upper graph, or set of 4 graphs, we have tip resistance on the bottom, friction ratio on the top. Going from left to right, we have water content versus tip resistance or friction ratio, and then suction versus tip resistance or friction ratio. And the first thing you notice is that there is a lot of scatter in the friction ratio data. Some consistency in trends, but there is a lot of scatter. And then, but when we look at tip resistance, there seems to be a very strong correlation between water content and tip resistance, or suction and tip resistance. Now I've added some data to this plot, and I'm gonna give a shout out to Dr. Tan at Terracon, who was, he was my first PhD student at OU. He did some really good calibration chamber tests, basically, which involves it's almost like a giant triaxial cell. Think of a triaxial cell with a 2-foot diameter soil sample that's 4 feet high. And what you do is you control the confining pressure on that bed and the vertical pressure. So you can control the state of stress in that soil bed. And then from the top, you can push a cone into it. It's called a calibration chamber. So this was a flexible wall calibration chamber, and Norman prepared soils to different water contents corresponding to different suctions, and then did CPT testing in that chamber. And so this summarizes the results of years of work with that chamber. Boils down to 10 data points, but each of those data points probably took a month or two to produce. But you can see there's very strong correlation between water content and tip resistance. And as water content increases, as we would expect, tip resistance decreases. And similarly, the inverse is seen for suction, which we expect. As suction increases, tip resistance increases. So clearly there's an effect that we need to think about when we're doing this type of work in the unsaturated zone. On the right, you see a table. It just summarizes the slope and intercept and the coefficient of determination for all of those different trend lines. If you look at the coefficients of determination, they are generally pretty good. Most are above 0.5, some are up close to 0.7, some are lower, but generally pretty good. So we actually, this is published if you're interested in the paper. We actually went and collected all of the data we could from the literature at the time that we wrote this paper. And oh, I'm sorry, I didn't explain the lower two graphs. These are the same, except we have normalized the tip resistance by the vertical stress. And that's because just like SPT, if you push a cone in a soil profile, let's say it's the same soil from top to bottom, the tip resistance will naturally increase as a function of depth. So if you want to compare apples and apples, you have to basically factor out the effect of that vertical stress. So that's what the normalization is meant to do. And the coefficients may be slightly better for that. And these are on a log scale. So if you ever want to make your data look better, plot it on a log scale. It tends to tighten things up. Okay, but clearly this is, in my opinion, this is real important to think about. And there's not a ton of data out there. I think more and more there probably is. I haven't done a good search in recent years, but I think more and more people are looking at these things, which is good. And here is a bunch of data that we collected from the literature. I think there was 11 different sites. The nice thing was it included some sands. And so this plot shows normalized QC and then QC down here for sandy materials. And you can see that QC increases with suction, but if you normalize by vertical stress, the increase is not as much. It's almost flat. So this tells you the suction is not as critical for sands as it is for clays. The clays, these slopes are very steep. Or I should say the finer grain soils. There's other soils mixed in there, but the sandy soils are going to be less sensitive. The lower PI, sandier materials are less sensitive to changes in moisture content and suction. So at a sand site, you're not as concerned, but you still should be thinking about the influence of seasonal variations in moisture. Okay, so that's some data that shows what we can expect for different soils. Now, you could use these plots in essentially the same way as I did using my 10 sites, my correlations for the SPT. My N160 plot that I used to estimate change in friction angle and modulus. You could use these in a similar way. and not necessarily looking at the magnitude of QC, but if you know on a given date, actually my other plot maybe is better to demonstrate this. If you know on a given date that, you know, you were in unsaturated profile and your water content was 15%, and you want to know what happens, you know, I know it's pretty dry, and if I reach saturation, I'll be closer to 20 or 25. Well, you can look at these slopes, and if you want to be conservative, pick one that's higher, or if you want to be less conservative, or look at the soil types and see what you compare to most closely, and then use that slope to predict how your QC will change. So if I get a delta over that line from 15 to 25, apply that delta to your QC for the same moisture content for a similar soil. Again, it's highly empirical, but the alternative is to do nothing and not think about it, which you may get away with. But I think my approach to engineering is I want to know exactly what's going on. I want to think about everything. Ultimately, it may not affect what I provide the client, but it might. And I have a better understanding of how things are changing. Where this becomes more important potentially is in a forensic investigation, where just approximating, assuming saturated conditions or this or that, that's not enough. You're trying to understand how something failed. And a lot of things fail under unsaturated conditions. So to evaluate what happened, you need to use the mechanics that apply to the problem. So, okay, so that's data that we've looked at, some collected ourselves, some good folks in the literature have provided. And now we're going to see how this affects soil properties used for analysis, as well as how it might affect the performance of our structures. So again, we'll use a very simple problem of bearing capacity based on estimated total stress strains or undrained strains. And so again, I'm just using the simple Terzaghi equation, and this time it's just for a strip footing. I don't have the 1.3 factor out front. And so with the cone, you can estimate undrained strength using this expression here. And again, I would caution you, this is probably more relevant for saturated clays than unsaturated clays. But if we don't have any laboratory measurements and we want to do stability analysis, we still may want to estimate strength. Even if it's not a highly technical analysis, it gives us some basis to make recommendations. So we'll do a total stress analysis. And I'm going to estimate total stress strength using this equation, which is well known for the cone. It's the tip resistance minus the vertical overburden pressure at the depth you're considering the tip resistance, and then divided by what's called the cone factor. What's interesting about this equation, and what I like about it, is that is the same equation that you can use to calculate the tip resistance on a pile. If you solve this equation for QC and assume that's QT for a pile, that's essentially the end bearing equation for a pile. So you're treating the cone like a little pile, and the tip resistance is, but you know, the difference is for a pile, this would be N sub C for a pile, which for a deep foundation is 9. The factor's 9. For the cone, it tends to be on average 17 or even higher. I found for our clays, it's more reasonable to use something a little higher. And that probably has, yeah, go ahead, Jim.
Some of my work, I found that the NK value could get up into the 30s.
I believe it.
Because we're so over consolidated, most of our damn stuff is consolidated. You know, I found in the clay soils in the eastern part of the state, they're stiff, and the values were close to even. I had some at 35.
Yeah.
Some in the low 30s.
Did you compare those to lab tests to figure that out, or what did you?
Well, that piece is to calculate the
Ah.
range and the damn NK factor.
Oh, okay.
That's what
No, I believe it. I believe it's that high. You'll see in the example that if I use 20, the estimated undrained strengths are still pretty high.
Yeah.
But the tip resistances we get in some of these clay profiles tend to be very large. So yeah, you do want to be careful. But again, this is just for illustration. So I'm using 20. You know, back east, we'd always use 17, but we were generally testing truly saturated clays with, you know, low to moderate OCRs. It's different. It's different out here. So that's a good point. I'm glad Jim brought that up. All right. So for this analysis, I just picked two profiles that kind of represent the extreme at our Goldsby site. So here's my wet period QC values, and here's my dry period. You notice all of these tend to match a little better up top. So probably that variability we saw before, that divergence, probably related more to the test type. These are also done. Nice thing about the cone is you can start at the surface, so you can capture that gradient and the moisture condition and its effects. So, all right, so did the analysis with these, and this time I did it for two scenarios. The first scenario being if you did your CPT during the dry and recommended your allowable based on the dry season results. And then conversely, if you did it, your CPTs during the wet season and made your recommendations during the wet season, what would happen when the soil dries out? That's obviously the preferred scenario, but not always the one that we're faced with. So here you can see the results. Again, the allowables are very high, and that's because the ultimates are very. So no, not that we would necessarily give allowable bearing pressures of that magnitude, but that's what the data bears out in terms of the strength analysis. There are other considerations, again, like settlement, that we have to consider. But you can see if you design dry and then you get a wet period, and you keep the same recommended actual bearing pressure, you're going to end up with a change in factor of safety of 3, or from 3 to 1.2. That's a little scary, assuming that we've given that high of an allowable pressure, but that's what the soil theoretically would bear based on those strength estimates. And again, taking Jim's point in hand, maybe that 20 should be a 30 instead of a 20. Okay, and then in the lower computation, it's just the opposite. So we do it during the wet. We base our actual on the wet, which would be 2.9. If the soil dries out, our factor of safety is going to increase. So this illustrates that clearly it's more desirable to do your in situ testing during the wettest period expected for that site than during the driest. The problem is, as you know, we don't have control over when we do this stuff. I mean, outside of the time span of 2 weeks, we don't have much control. So that's the challenge. And then the other thing I wanted to show you, here's the variation in friction ratio. So if I look at the average friction ratio for those two time periods, and I use it to classify the soil, this is what I get. My dry season gives me zone 7, which is silty sand to sandy silt. And my wet season gives me zone 4, which is silty clay to clay. So be careful with your profiling in these unsaturated zones. Okay. I think that's it for this particular. Yeah. Any questions on that particular section of the presentation? In situ testing, mainly SPT and CPT and unsaturated soil. I hope there's something of use in that you can take home with you and be thinking about in your own practice. Next, we're going to talk about Tarek's favorite topic. In fact, he's volunteered to come up and take my place for this section. Just kidding. I wouldn't make him. No, but actually, Tarek deserves a lot of credit for what I'm going to show in this particular section of the presentation. This was Tarek's dissertation topic, did a lot of good work. Dr. Nevis helped us out a bunch with the seismic CPT measurements. So we're going to talk about this subject for a while. We'll go for about 15 minutes and then we'll take our last break. And then everybody should chug a cup of coffee to get us through the last part of the presentation. All right, so seismic velocity in unsaturated soils. So first, I'm going to talk a little bit about this research because this topic may be more new to some of you than others. And just to give you some sense of how we approach the study. So first of all, you might ask, why were we interested in this? So what got us thinking about it was clearly the moisture contents impact our in situ test results because it's affecting the properties of the soil. So that probably translates to the fact that it's going to impact other properties like shear wave velocity or small strain shear modulus. So which shear wave velocity depends on. So we thought, okay, this is a good topic, but from a practice point of view, why would we be interested in that? And I think one reason would be because we can base seismic site class on shear wave velocity measurements. So if you look at the IBC or various codes for determining seismic site class, there's basically three approaches you can use, three general approaches. You can look at a weighted average shear wave velocity itself, which is probably one of the better approaches since shear wave velocity is directly related to ground response and seismic analysis. You can use a weighted average N value, and you're basically weight averaging over the upper 100 feet of a profile. And then finally, you can look at the weight averaged undrained strength for clay soil profiles. So SPTN values are quite simple to use and often used, but shear wave velocity is probably a more precise way to analyze seismic site class. Those of you who have seismic cones, I know Jim does. Do you have a seismic cone? Everybody does. Maybe you've used VS to estimate seismic site class. So the question is, again, will the site class change if the moisture conditions change in the upper profile? And it's possible, depending on how significant the change and depending how thick that upper profile is, it's possible you could jump from C to D or D to C, depending on seismic velocity measurements during wet and dry periods. So that was one motivation. The other is that seismic velocity can be used to estimate the small strain shear modulus, which is incorporated into ground response analysis, such as using program shake, where you're trying to determine how the ground is going to respond to seismic excitation. So those are the two primary reasons that motivated this work. So what were our goals? Well, we wanted to investigate the impact, first of all, of moisture content and suction. Those two go together on the shear wave velocity measured with the seismic cone penetrometer. And so again, how does that delta W or that delta suction, how does it affect this VS? Those of you who are not familiar with the test, basically you produce an excitation at the ground surface, usually with a big metal plate that's embedded in the ground, and strike it with a sledgehammer. That causes a shear wave to propagate to the measurement location, which is going to differ. So you push your cone, you stop, do a shear wave velocity measurement, record the numbers, or computer records them for you, push it to the next depth, do the same thing, and you can use the difference in the travel time of these waves to estimate the shear wave velocity in the layer between those two locations. It's fairly straightforward and simple application of wave propagation velocity, or time of arrival, to estimate shear wave velocity. So that was the first thing. We want to see, okay, how is this VS going to change if the soil moisture changes in those layers? The second thing was we wanted to do some work in the lab. And, you know, basically doing research in the field is great. The problem is, even if you do use the same site and do multiple soundings, there's a lot of variation in the measurements. So there's always a lot of scatter in the results and in the comparisons that you make with water content and suction. There's a lot of scatter. So to get past some of that inherent scatter, Tarek did a bunch of testing in the lab. So in the lab, you can measure shear wave velocity with something called bender elements. And you essentially do it in a triaxial type setup. And so you put your sample in between a top cap and a platen, and you create a little excitation with those bender elements. They're basically little piezo ceramic fins, if you like, that stick into the soil, and you excite them and they flip and they produce a wave. And then down in the bottom, you detect that wave, and you can get the arrival time and use an oscilloscope to look at your waves, and you can get your first arrival times, and you can calculate the shear wave velocity based on arrival time. So the reason we did this is we wanted to use samples that were highly reproducible. So we created our own samples out of the same material and did a bunch of different tests, where he did a bunch of different tests on soils with different sand and clay contents, and then different water contents and suctions. So the idea was we'll have a much more controlled set of data to look at the behavior. Now, I'm not going to share this data with you today, although you can look at his thesis. It's very good data. What I'm going to focus on is the SCPT data, the data we got in the field. But I bring this lab measurement up because another thing we wanted to know is how well data from the field compares with data from the lab. So, you know, how good is the comparison between field and lab shear wave velocities? So to do that, at 3 test sites, we took Shelby tube samples essentially from the middle of the layers over which we measured the shear wave velocity. So shear wave velocity, you know, you might be measuring shear wave velocity. It's an average over that 3 feet. But we took a Shelby tube sample from roughly in the middle and took a 6-inch sample out of that 3 feet and did a shear wave velocity measurement in the lab. And we wanted to compare them to see how robust those field and lab measurements are, see how well they compare. So that was another goal. And there was a secondary goal to that I'll describe when I show you the data. And then ultimately, once we've studied this, the idea was, could we then, again, just like we did for SPT and tip resistance, could we develop a method to predict changes in shear wave velocity as a function of changes in water content or suction? Okay, so that was basically the motivation and the goals of this research. And I think it does have practical implications. And again, there will be some takeaways I believe you can use. Okay, so a little theory. I'm going to go through this relatively quickly, but I'm going to show you one second-order differential equation. I'm not going to explain it in detail, but this is sort of this equation is the reason for why shear wave velocity is important to us. So this equation describes particle motion due to a compressional wave propagating through a rod. So it's a one-dimensional wave. Okay, this is the equation for a torsional wave. So if you let the rod twist. So this wave depends on, in some part, the shear wave velocity. So if you look at these two equations, again, this describes the variation in particle motion at any point in that rod as a function of time. That's what the solution of that equation, that's what it tells us. The speed at which the wave propagates that's causing that displacement is actually given by this coefficient G over rho. Now, G over rho, that's shear modulus of the material. Rho is the density. That is not wave propagation velocity. It's equal to the square root of that term. Okay, but the wave propagation velocity is what we're interested in, because we're not measuring particle motions with the SCPT. We're measuring velocity that the wave is propagating through the medium. And that's what we're using to back out shear modulus or to determine seismic site class. So that's what we're interested in. So that's why I show this equation. This is a very important relationship. This is a fundamental characteristic of the medium or the soil that the wave is traveling through. So the wave propagation velocity is equal to G over rho. G is the shear modulus, but we refer to it as a small strain shear modulus because a propagating wave does not create much strain in the profile. Right? So and the shear modulus tends to decrease as the strain level increases. So if I measured shear modulus in a triaxial test, it would be much lower than the shear modulus I measure from shear wave velocity movement. That's why it's called G max, because it kind of represents the maximum shear modulus for the material. Okay, so we're going to go about trying to measure that with our SCPT, but I think it's important to understand the relationship between VS and shear modulus and rho. Now, looking at this equation, you would say, okay, the VS is going to increase if shear modulus increases, and it's going to decrease if density increases. But the effects are not the same, right? And the reason is the shear modulus increases with increasing density. So while density increases, it's going to cause a reduction in shear wave velocity. It simultaneously increases the shear modulus, which causes an increase in shear wave velocity. And that increase, due to the increasing shear modulus, tends to outweigh significantly the reduction in shear wave velocity due to increasing density. So I have a couple plots that illustrates that. And without going into great detail, what I did is I took a sort of universal equation for G max based on a publication by Bui et al. This is a general equation that relates G max shear modulus to void ratio, which we can relate to density, and effective stress state. And so I just substituted in the density. So these are equivalent. I just wanted to look at it in terms of density. And then I stuck it into our VS equation. And so using this, I could see how variations in density affect shear modulus and affect VS. And that's what this plot shows. So this is our baseline, right, at a density of 1400. And given these parameters, specific gravity, 100 kPa, effective confining pressure, that equation gives me this. Now, if I increase density, it's going to increase G simultaneously according to this equation. And this is what's going to happen. So even though density is increasing, I'm getting a significant increase in shear wave velocity. The contribution from density is this. It's negative, right? We know it's inverse. So this is what happens. This is the reduction due to increasing density. And then this is the change we get due to increasing shear modulus. The net result is that's how the shear wave velocity is going to increase as a function of density. So even though it's inversely related, that increasing density only causes a small effect relative to the change in shear modulus that results from that increase in density, okay? The reason this is important is because we're testing variable density materials, and we noticed that there is an effect of density, but it's far outweighed by the effect on shear modulus. The other thing of importance is the effect of confining stress. So in the field, different depths are going to have different confining stresses. Effective confining stress is going to increase with depth. And the confining stress has a significant impact, right? As effective, according to our equation, as effective stress increases, you can see shear wave velocity increases significantly. And then those are the variations due to increasing density. Why is this important for our unsaturated soil? Well, there is confining stress in the field. It comes from the overburden pressure. And now we have to think of it coming from the changing suction. Increasing suction is going to increase confining stress at whatever depth. Increasing depth is also increasing confining stress. So we need to be thinking about these things when we're looking at our shear wave velocity data, analyzing it, at least in terms of the research that we did. Okay. There's Dr. Neville's lovely cone truck. And again, he was instrumental in this work. We appreciate it. And Metco contributed a lot as well. We appreciate them. All right, so some of the things we did. So this is an overview. We visited 9 field sites. There was a variety of soil types involved. So this is the field portion. We did 2 CPT visits per site. We tried to target wet and dry seasons. I think one of the wet seasons was so wet we couldn't get the rig in, but in any case, and we generally accomplished that. We did 3 soundings per visit. We did soil sampling so that we could get water content, and then we did total suction measurements. And the idea was to investigate changing moisture content and suction on shear wave velocity. So of these 9 sites, 3 sites showed significant differences. It doesn't mean the other sites weren't important. It's just meaning the contrast in the data was not enough to be able to say conclusively, what was going on. So we looked at what I'm going to show you is 3 sites to show the most contrast in the results. And so here they are. This is the first site. I think that's Watanga. I call it WA. You got a highly plastic clay. Again, you'd expect those clays to be more sensitive to suction changes. There's our variation in suction, significant, and our variation in water content. Now, obviously, this is down to about 2 meters, so didn't see a lot of change below that. And you'll notice the shear wave velocity correlates pretty nicely to those changes in water content and suction. It's that last plot there on the right. Another site, this is the Wewoka site, I believe. And again, we've got some significant variation in moisture content and suction. There's our moisture content. This is our suction. That psi is the symbol for suction. And again, we see a corresponding difference in shear wave velocity. And then finally, our last site, which I think is the Fears Lab, we saw some significant differences there in the moisture content and the suction and the shear wave velocity. Now, some of the other sites, we just didn't see enough difference in water content or suction to make a big difference. But at these sites, there were some significant changes, and it affected the results. So the question is, okay, we know it can change. What do we do with this data? Well, we start plotting things and seeing if there's any correlation. And so for the field data, we plotted water content versus shear wave velocity. And then we plotted total suction versus shear wave velocity. And the water content, at least for 2 of our sites, is strongly correlated to shear wave velocity. You can see the coefficients of determination are both above 0.9. The other site, not so good, but the trend is in the right direction. So again, here's a very simple way to think about how to estimate changes in shear wave velocity based simply on changes in water content. So if you're testing in the dry and you want to see what happens when it gets wet, estimate your future moisture content, or look at a delta of 5 or 10% and see how that shear wave velocity might change just using one of these slopes. You know, it's empirical and it's highly uncertain, but it gives you a tool to think about this problem. And as we collect more data, our correlations will be better refined, and you can create your own. I mean, even at a particular site, sometimes, like if you're in a fairly uniform material with depth and your moisture content's varying with depth, you might be able, on that given date, plot moisture content versus shear wave velocity and see some rough correlation, assuming the material hasn't changed appreciably over depth. And again, you may have to consider overburden pressure in that analysis because that's going to affect your shear wave velocity. You follow me? So you can develop, begin developing correlations just like I did with the SPTN values. Start plotting shear wave velocities versus water content for different soil types, and you'll probably see some trends. They'll be scatter, but you'll get some sense of how things might change. We also plotted it versus total suction. The correlations are not as strong, and that's for a number of reasons. Water content is a much more robust, reliable measurement than total suction in the chilled mirror hygrometer, and it is impacted by osmotic suction. So there's more uncertainty and there's more scatter. But the trends are in the right direction. Okay, so in our laboratory investigation, this part of it, again, the idea was to compare shear wave velocity measurements from the field and the lab. So I'm going to jump right into the results. And I thought this was fantastic when I saw this, because what it shows, so again, looking at this last figure, this is the SCPT shear wave measurement in the field. That's from the Shelby tube sample in the lab, which tells me that both of these measurement techniques are quite robust and reliable. Now, I would expect some variation between field and lab because of the fact that the field measures shear wave velocity over a significant layer thickness, maybe 3 feet in our case, whereas the lab measurement is from the center of that layer. So I would say that at these sites, that generally there is fairly good uniformity over those layer thicknesses, so that lab measurement was representative of that layer in the field. If you got a lot of contrast in your layering, the agreement may not be so good. But for our sites, it was generally very good, which really encouraged me tremendously, because it's rare that you see such good comparisons between field and lab measurements. But shear wave velocity, we saw it. And this site, again, that's the first site. This is site 11. This is where we saw the most contrast between the two, and only for that upper depth at 1 meter. And again, this could be related to the variation, the heterogeneity in that upper meter. So, we're not capturing that with the single sample in the center of that layer. But very encouraging. And then the last site, again, very good agreement. So I found this to be remarkable and highly encouraging, because, this gave me great confidence in shear wave velocity measurements and their use in practice. Okay, so what we did is we took advantage of that similarity. Was there a question? Oh, Jim, I'm sorry. Go ahead.
I was going to ask you, did you compare the percent fines you measured in the lab with the predicted percent fines from the cone correlations?
Not for this. No, we did not. We could. We did this was part of a broader study for ODOT looking at CPT correlations for soil. And I can't remember, we looked at percent fines in those correlations, but certainly it's something we could do. But we didn't, Jim. But these soils, these soils are the same soils, right? Except one comes from the middle of the layer, and then in the field, we're looking at a 3-foot layer. So we're assuming that that lab sample was representative of that field layer, which I think in our case was true because we got such good agreement. The other thing that's important, there are a few published papers that compare field and lab measurements similar to what we did. And what's critical is to the lab measurements is you have to apply confining stress to your sample that simulates the confining stress at that depth in the field. And we did that. Confining stress is critical. If you don't use confining stress that simulates the field, you get totally different results. And some of the data and literature shows that. So that's an important part of this comparison. Otherwise, it was the same moisture content, samples from the same day, and the comparison was great. So I was encouraged. So the next thing we did is we said, okay, since the lab and field compare so well, we can use lab measurements as a surrogate for what will happen in the field if the moisture content changes. So what Tarek did was he took each of those Shelby tube samples that we tested at the in situ condition, which is represented by the inverse triangles. And then it's the solid circles. And then he wetted those samples in a controlled humidity environment, which basically means he stuck them in a sealed container with a salt solution, having a known osmotic suction. They weren't touching the solution, they were sitting over the top, and that forced a change in suction and moisture content. He let them change and he measured shear wave velocity in the lab, and then he wetted them and he did the same thing. Or he might have wetted and then dried. I think he wetted and dried. Yeah. And so what we got is a range of shear wave velocities versus water content and suction. And as we expected, there's a big difference. The difference between this and the field testing is this is highly controlled in a laboratory environment. And so this was highly useful because from those lab measurements, we could extrapolate what would happen in the field with our CPT measurements if the moisture content changes. So if we did it in a controlled lab environment, or we didn't have to depend on the weather to make those changes for us. So that's the data we collected. This is the site 11. And again, these are the ones in the lab where we varied the moisture content and suction and measured shear wave velocity. So we took all this data and we started summarizing the results and seeing what we had. And so the first, and initially we took all of the soils and lumped them together from all of the sites. We didn't parse by soil type. We just lumped all the data together and looked at shear wave velocity as a function of water content. And as expected, there's a very strong correlation for this laboratory obtained data. And coefficients of determination are very high. You'll notice two sites are very similar in terms of their trends. But what we call site 10 tends to have higher shear wave velocities for a given water content. And part of that can be explained by the soil water characteristic curves that are shown below here, the relationship between water content and total suction. And over there, we have water content versus estimated matrix suction. What you notice is that if we look at it in terms of suction, all of the data tends to converge at a total suction of 200 kPa. And that's essentially, in terms of matrix suction, that's where we're approaching saturation. So, but at higher water contents, there's a significant difference that can be explained by the difference in the soil water characteristic curve. For this site 10, you get much higher suctions for a given water content, whereas the other two site soil water characteristic curves practically plot on top of each other. So again, this emphasizes the importance of matrix suction on the shear wave velocity being much higher for site 10 due to the higher suctions at the same water contents. And again, now we have actual trend lines that we can use to predict changes in shear wave velocity as a function of water content or suction, which we can use in our analysis. We then parsed it by soil type. In this data set, we've only had CL and CLML type soils. We might have had a few CH, but not enough to develop their own trend line. And I think the regression coefficients improved slightly for CL, but might have decreased slightly for CLML compared to the all soils plot. But we see similar things. Okay, now, because this was a research project, we wanted to analyze the problem in a little more depth. And actually, the one thing we're not accounting for in these plots is the effect of confining stress. These are at different depths, so there could be some small effect due to confining stress. Now, it's not over a huge range of depth, so changes in confining stress weren't dominant, but theoretically, we should include that in our expression for stress state using a Bishop type stress state or two stress state variable approach. And so what I've summarized here is different models from the literature that show shear wave velocity. For example, this one here by Sawang Surya et al. 2006 uses the Bishop effective stress. So it has shear wave velocity is equal to this coefficient A times the Bishop effective stress raised to parameter beta. And then the two stress state variable approach might look something like this, where we have the net normal stress and suction treated independently. We sort of took a hybrid approach because we didn't have a lot of information about the degree of saturation of our samples and how it changed. So we simply just incorporated a two stress state variable approach, but simplified because we didn't want to have to calculate these four coefficients. We just said A times these two stress state variables, the summation of times beta. So it's kind of like the Bishop approach with chi equal to 1. In any case, as we would expect, that represents the behavior very well. So if we instead of water content or suction, we plot shear wave velocity versus this sigma minus UA and UA minus UW, you get some very nice trends that you can use, again, to model the shear wave velocity. Now, ultimately, from a practical point of view, this model may be less appealing than the water content approach, which is fine. I think the idea is to recognize shear wave velocity depends on water content and suction, and to some degree, it depends on the overburden stress. And then to think about the fact that if moisture contents change, that's going to have an influence. And how does that affect your determination of seismic site class? It may not. It just depends on how much of the profile is affected. It's only a small portion of the profile may not change the seismic site class. But if it's borderline CD, it could change it. And then the final thing we did was just develop some correlations between those fitting equations for our model. But I would say they're uncertain and relatively weak because we only have 5 data points, but it's a start. The trend lines are in the right direction. And so, maybe we can build on this with future research. So I'm going to leave you with this in terms of our shear wave velocity discussion. And that is, you can, the approach you can take, there's different approaches, but the main thing is, if you're doing shear wave velocity measurements, or I should say any, you could almost apply this to any of the testing techniques we talked about. One thing you can do to improve your knowledge of unsaturated behavior is make sure you're taking plenty of water content specimens so you can map the water content profile of your soil. Even if you don't want to do Atterberg limits and grain size tests on every sample, at least do a natural water content test. That's tremendously valuable. And then you have something to compare to your field results. And then, you know, if you can, do more Atterberg limits, do more percent passing 200 tests. And if you have the capability, measure total suction. Any additional data is going to help you get a handle on this problem. I know some labs may only do, you know, Atterberg limits, 1 or 2 in each of the upper layers or whatever it is, some more, some less. The more you do, the better information you're going to have to predict changes due to wetting. And one example would be, you can use this. Remember, I showed you that empirical method for generating this curve. You need PI and percent fines for clay soil to do that. That's pretty low hanging fruit. From that, you could estimate suction, and you could use a model like this that considers normal stress or overburden pressure and suction. Or, you know, you could bypass this and go straight to a water content versus shear wave velocity plot, assume a slope for your particular data, and estimate how water contents or how shear wave velocity is going to change as a function of water to content. At this point in the state of research, honestly, I think this is probably the most practical approach to handling changes in shear wave velocity, SPTN value, CPT tip resistance. I think this is the most practical approach until our research is more refined and there's more of it. There's not a lot of research out there like this. And so it's hard to put a lot of confidence in models like this, even though they seem to work well for our data set. That's 3 sites. It's not enough. But again, you can build your own little data sets of water content versus these parameters, start to get a handle on how these things change as a function of water content. So you don't need to do all the suction measurement or even the soil water characteristic curves. To know you're in an unsaturated profile, at least get good water content data on the date of testing. I'd suggest every foot in that upper profile, but you know, whatever you get is good. And then estimate how that's going to change, and you can estimate a change in a property or test parameter. All right, that's my spiel on in situ testing. After a short break, the last thing we're going to do is talk about the influence of suction on laboratory testing. Yes, Ali.
All those variations in shear wave velocity have an active point, which is close to 0.
This is right.
And for seismic fluid class, the variation happens for 2.
That's right.
So do you think that's possible to make a seismic size class? Because it's
Probably most of the time it's not going to change, but I considered that question very carefully. And it can. If you have a borderline classification, that change in the upper 10 feet can impact the weighted average VS that you end up with and push you over the edge. And it also depends on the VS in that lower, you know, typically it's a base layer of shale or sandstone or whatever. So it can. Most of the time, probably not, but it can. So, you know, and that's kind of my whole philosophy to unsaturated soil mechanics. It's not always going to make a difference, but being ignorant is not a good thing either. So if you can recognize that it's not important, that's good. Doesn't change my results. Fantastic. I don't have to do anything different. But at least you know that it could. And there may be a situation where it does, and that's when you get bit. So yeah, and I think this is when we talk about volume change, if they invite me back to do this again, part 2, we'll dig into that because there is a lot of issues. You know, we all do PVR and these estimates of shrink swell behavior, but yet there's still a lot of problems with shrink swell behavior in commercial buildings where they've had recommendations to reduce PVR. Why is that? It's not necessarily that the engineers don't know what they're doing. It's because the methods that are used are not that great. That TxDOT method can be off considerably from overly conservative to way unconservative. You don't want to be unconservative when you're estimating heat. So, I mean, so my whole thing about unsaturated soils is that it's not always going to change things in terms of what you're doing now, but at least you have the knowledge and you know to think about it and appreciate it. And there may be cases where it does make a difference. So keep that in mind. So let's take 5 minutes, come back at 11:35. I meant to mention this at the beginning. I'm not going to cover all the laboratory stuff. I kind of knew that when I put this together. I wanted to make sure I had enough to cover the 4 hours. So in the presentation I moved the discussion on unconfined compression tests to the top of the laboratory discussion. And the direct shear test and triaxial test stuff I'm not going to get to today. But I think from a practice point of view, unconfined compression testing is probably more frequent than the other two. And so I think that's probably more relevant in terms of applied unsaturated soil mechanics. Okay. So 5 minutes, be back at 11:36 and we'll get it knocked out. And if you have questions, I'm going to leave some time at the end. So if you have questions or please write them down. If you don't have a question, come up with one.
They're in the corner of
So we are reaching the final push here. Let's see, that's up. And we are going to end. So we've talked mainly about in situ testing. You can hear me, Olivia? Okay. We've talked mainly about influence of soil suction on influencing in situ tests. But we also need to give some thought to how it might affect laboratory tests. And I'm specifically thinking of tests that you do on soils at the natural water content. Now, I think in terms of undrained strength, if you really want a truly saturated undrained strength, the only way to properly achieve that would be with back pressure saturation and a consolidated undrained triaxial test. But in a lot of our practices, we rely on unconfined compression tests. Now, the unconfined compression test, even for saturated soils, is not the greatest test for estimating undrained strength. And for unsaturated soils, it could have even more shortfalls. So we're going to talk a little bit about that. And again, we're going to do it through demonstration. We're going to look at how variations in undrained strength from unconfined tests taken under different moisture conditions at the same site influence the estimated bearing capacity that you get. And so this data was not part of a research project. We were fortuitously able to collect this data through our laboratory and in situ testing course over many years. This data represents about 13 years. And so in our course, we would take Shelby tube samples from our FEARS engineering test site. And the students would run CIUC tests on at least one sample, clay sample, and then they would do unconfined compression tests on the other samples. So over the years, we gathered a fair amount of data. And on the left, you see the unconfined compression test data as a function of depth, the green dots. And then you see the CIUC data. Now, if you look at the CIUC data, it's clustered much more tightly together because it's a high quality test and it's not prone to variations in moisture content or structure or strain rate, all the things that affect the unconfined test. There is one outlier in the CIUC data, and that's because that particular class wasn't as good as the other classes that we've had over the years. I'm just kidding. I don't know why that point is off, but it might have been just natural variation. Remember, these samples were taken in different years at different depths, so and there's some variability in the stratigraphy out there. So, but I'm calling that an outlier in my analysis. So, what we can see looking at this plot, and on the right you have degrees of saturation. You can see that the unconfined tests are either really over conservative or under conservative relative to what I call the true undrained shear strength measured under saturated conditions using the CIUC test. Okay, so also note that during this time period, the water table varied between 4 and essentially 15 feet below the ground surface. So moisture conditions were a lot different. So what I did is to analyze this further, I basically parsed the data out based on water table conditions. And so from the low water table times of testing, when the water table was up near the ground surface, those are the green points. So obviously we had much higher water content. And then when the water contents were lower and the water table was low, those are the blue points. So what you can see here is if you're doing unconfined tests on a soil, unsaturated soil, first of all, you're not measuring the true saturated undrained shear strength. You're measuring a total stress strength that depends on the moisture content at the time of testing that sample, which depends on when you obtain that sample, what season, was it dry, was it wet? Clearly, from a practice point of view, if you're relying on unconfined compression tests to measure undrained behavior in the saturated state, you want to collect your samples during a wet season because those are conservative relative to the what I call the true triaxial condition. So I would say the red would be the best data to do our analysis, but we don't always get to run CIUC tests. And then the blue is the worst case. That's a very unsaturated condition and the strengths are artificially high because of the suction in those samples. And again, if we do that comparative analysis of allowable bearing capacity based on those results, and in this case, we're going to call the CIUC the true values. That's the true saturated undrained bearing capacity. We see that the allowable bearing pressure is about 1.4 tons per square foot or 2,800 PSF, which is much more in line with what we might recommend locally. And then for the dry conditions where the water table was at 14 or roughly 15 feet, the ultimate is 7 and the allowable would be 2.3. But again, if we did the testing under the dry, or I'm sorry, compared to the CIUC, the true value, the factor of safety would actually be 1.8 if we recommended a Q allowable of 2.3. And that's relative to the ultimate capacity under the triaxial true saturated conditions. And then conversely, if we use the unconfined data that we got when the water table was high, we'd underestimate the strength and the bearing capacity, and we'd actually end up with a factor of safety of about 6.9 compared to the triaxial test results. So the lesson here is, and this is the last lesson for today, think about the implications of moisture condition, moisture content on your laboratory testing if you're doing it at the natural water content. And that could apply to unconfined compression tests. It may apply to direct shear tests, whatever the case may be. If you're testing a soil that's unsaturated, has moisture in the lab, even if it's a sand with little moisture, that moisture is going to create suction and that's going to affect your strength parameters and potentially your compressibility parameters. So, all right, I'm going to, in the interest of time, I want to leave a little time for questions. Oops, I did it again. Didn't do what I wanted to do there. Excuse me, hang on a second. I don't know why that keeps happening. What did I do? I think I somehow exited out of my, all right, I guess I'm doing this old school. So the rest of this digs a little deeper into lab results for unsaturated soils. I didn't expect I would get to everything, so I'll leave it to you to look through some of that, and I can provide some references if you're interested. Okay, so let's just briefly review the takeaways, and then I'll leave time for questions and discussion. And okay, so first thing is when analyzing structures in contact with unsaturated soils, consider the implications of increasing water content. I think we've gotten that message across. When interpreting field tests, consider that estimated soil properties will change due to changes in moisture content. I think we've established that. And then when interpreting laboratory tests on samples at the natural water content, consider how soil properties may change due to changes in moisture content. All of these things are within your reach. What can we do? Take natural water content samples, as I said, at frequent depth intervals. start building your own internal correlations, determine the water table location accurately. And then, if you can do more index property tests on your samples, that helps to build your correlations in your database. And then the other thing you can do is pay attention to the weather and climate in your area. We have great weather data at our fingertips. We have the Mesonet. We can look at rainfall histories back many years. We have a drought monitor. We can tell whether we're in a severe drought or minimal drought. Lots of things we can do to get a handle on what the moisture condition we're in. If we're in a wet condition, you're probably in pretty good shape. But if we're really dry, then you need to be, thinking about things. And since a lot of our work happens in the summer, we're probably often in a dry condition. But a drought would be severe, the worst case, when we're in a extended drought for periods of years. That has a profound influence on the results of your tests. And what can you do? Well, use some of these techniques that we've talked about today. You can estimate soil water characteristic curves empirically if you want. You can measure suction pretty simply. Filter paper's low-hanging fruit, not an expensive test to execute. A little time consuming, requires some expertise, but there is an ASTM standard. Invest in a chilled mirror hygrometer like the WP4. They're a little pricey, but you can get some good data if you're interested in that. And then when you're doing in situ tests, estimate how things are going to change if moisture content changes, if you're worried about it. And then perform your geotechnical analyses for current and expected moisture conditions. If you're recommending 3,000 PSF allowable bearing pressure for a footing, would you do that for the wet period if you knew the N values were going to change from an average of 12 to 4? Maybe not. So, just be thinking about these things and their impact. And the other thing, the last point is to remember conservatism is warranted because there's a lot of empiricism in all this. We don't have a huge database yet, a research database on this topic. It's a fairly new topic. There hasn't been that much research, but we do have some data that's helpful and gives us an indication of trends. And you can use it, but just use it cautiously. All right, that is it. I hope you found something useful in today's presentation. I probably created more questions than answers, but that's the nature of this topic. I find it extremely fascinating, and I use it. I do a fair amount of consulting, and I use this stuff all the time in my approach to analysis. So with that, someone give me at least one question from this audience. Anything?
On the back to the cone testing.
Yeah.
I always thought about the idea of just reducing the cone tip by like 20% if you're going to have to make a guess of something.
Yeah.
I mean, that would be empirical, but
I think that's.
But it's an idea better than not doing it.
I think it's a great idea. What I often do when I have SPT N values in an unsaturated profile, I reduce them by 33%. Yeah, just a third. That's my approach. Why? Because that's kind of the extreme of what I've seen in my data sets. It could be more though. I mean, it just depends, but I think any consideration is better than no consideration. But I think you could look at some of these plots that we have, like QC versus water content, Jim, for the different soil types. And you could say, okay, I'm dealing with a silty clay, a CLM, or whatever it is. You can look at some of those trend lines in the data and you say, oh, okay, so their QC at this moisture content went from here to here. Well, that's a change of 40%. So I'm going to use 40% in my approach. Okay. So it's highly empirical, but it's what we have right now. If we want to start incorporating this into our analysis, I mean, we can do something. We don't have to do nothing. And whatever you do is going to be conservative. over just going with what you have on that particular test date. Unless you happen to be a very saturated wet condition when you test, then you don't have to worry too much. That makes sense? So I think 20%, that's better than nothing if you expect there to be a change, an increase in moisture content. But I think we can get a little more scientific if we look at those QC versus water content.
You know, it goes back to what they call the normal year. 8 years out of 10, you're going to have a condition pretty good. Then you'll have 2 that will bust the bubble.
Yeah. And we don't have control. So I see Ade had his hand up, and but either one of you. Let's start.
Oh, just to make a comment, it's very important that you do what you're doing, because it doesn't matter if you're in the desert out there somewhere, where it's conditions are pretty reliable for 90% of that. What about the other 10?
Exactly. Yeah.
The other 10.
Yeah. And that, you know, there's a lot of good unsaturated soil mechanics in practice in Arizona. They've embraced it pretty significantly in that area. And that's because they have to, it's a real problem. They have to deal with it. Like you said, they're arid or semi-arid most of the time, but you get a gully washer and it changes things up, right? So, yeah. Adi?
You know, just piggyback right on what Rick just said. It was exactly what I was discussing with Brent, not just outside now. That, you know, you go to the western part of the state, there's a reason why the bridges are not as span and you don't see water.
Yeah.
Because when you get out flood, it can really be significant.
Yeah.
You don't see much now, but it can happen. And plus, we really should be able to anticipate this thing from you stress on taking a lot of the moisture content in the profile.
Right.
I mean, if you really know, you know, look closely, you're able to correlate that to your other bulb, your plastic limit, when you know where you are, you know where you are in a high saturation condition than in a unsaturated condition.
Right.
You know, it gives you a good idea of, oh, I should be concerned here, or
Right.
maybe I'm close to being saturated. So, you know, the data I have right now, maybe.
No, I agree. I think that's a great point, Adi. The index properties, and in particular, liquid limit, plastic limit, and then natural water content, they tell you a lot. If you're close to that plastic limit or below it, your liquidity index is less than 1, you probably need to be thinking about expansion potential and how much heave you're going to get. And, you know, we've all developed that intuitive instinct for looking at that, and that's great. Yeah, you can take it a step further and start thinking about the impacts on your tests as well. So, other questions? Okay, so if you have additional questions, feel free to send those to me by email. Or if you're interested in any of the publications that I've talked about, I can either point those out to you, or if I have a copy, I can send that to you. Adi, yes.
Will your presentation be available?
Yes, they're gonna post it somewhere. Olivia said they'll post it somewhere. And then my last thing I was saying, oh yeah, so I'll be traveling next week, so give me a couple weeks. If you put in a request for a paper or something, give me some time to get that back to you, but it won't be too long. Okay. I really appreciate those of you in the physical audience and those of you in the virtual audience. I thank you for attending as well. I hope it was beneficial for you. And with that, I will say goodbye and have a great rest of your day. Thanks.